nanotechnology having the medium efficiency, so we can increase efficiency of this kind of solar cell, this generation solar cell. And from this graph we can see the NREL is a very well-known, world famous lab. They are working on this third generation solar cell. And emerging PV, in the emerging PV technologies, the dye sensitized solar cell is the very is the first one, and in the emerging technologies. So that's why we are working on the dye sensitized solar cell. And the introduction of dye sensitized solar cell is that the dye sensitized solar cell and the grid cell solar cell is invented by Professor Michael Ritzel in 1991, and he got the Millennium Prize on this invention. And he borrowed this idea from the photosynthesis in the plant. And after that we have the motivations of this kind of solar cell, as this is the low cost technology having the higher theoretical efficiency of 32%, and the powerful indoor applications, current fervently research topic suitable for the flexible substrate, and indoor performance, having the low energy manufacturing process and the ecological friendly. So that's why these all are the motivation to enhance our research on dye sensitized solar cell. And the basic structure and the principle of the dye sensitized solar cell is that actually this is the this kind of solar cell having the two electrodes. One is the photo electrode or photo anode, and the other part is the counter electrode. And these both electrodes is sandwiched between the electrolyte. And in the most important part of this solar cell is the photo anode. In this photo anode, the main part is the titanium, and this titanium structure is absorb the dye, which is absorbed is uploaded to absorb the sunlight from to enhance the efficiency of solar cell. So in this structure we can see that titanium layer is acting as a photoanode, and the dye is covalently bonded to titanium, and the redox iodide electrode is sandwiched between these two electrodes, and the platinum coated FTO glass is acting as a cathode. So in this kind of solar cell, in this traditional solar cell, the drawback of traditional solar cell are actually this kind of solar cell having the lower surface area of titanium nanoparticles, and the random part for the injection of electrons. And the third one, the main drawback of this is that carrier loss through recombination. So our objective is that we may enhance the surface area of this kind of solar cell by utilizing the other nanostructure, and after that we can increase the surface area as well. And after that we can also have another option for the state part for the fast motion of electron. And the third one is the maximum light harvesting can be achieved to improve the overall power conversion efficiency. And the fourth one is the low recombination rate to increase the current density. So these all are our objectives. So we can achieve our objective by utilizing the different optimized nanomaterials. So first of all, why we use the titanium and the nanostructures? As the titanium nanostructure, as the titanium material is the very low cost and the non-toxic and also the transparent, almost 80% in the visible region, high internal surface area and the porosity. And the fifth one, the chemically and electrochemically stable, and the last one is the suitable surface chemistry for the dye sensitizers. And after that, advantages of the nanostructure. So in this way we can see in this in this century we are using the nanotechnology as the nano as if we use any of material in the bulk way, so the efficiency of that material is not as efficient as when we use the when we use that material in the crystalline way. So as the advantages of the nanostructure are the higher interconnected surface area and the light scattering effect, and the third one is the fast electron transfer process. So in this diagram, in this figure, we can see that if we use the if we use the single crystal titania, the absorption and the IPC of this titania is about 14%. So when we use the nanocrystalline titania, the efficiency is enhanced, is dramatically enhanced, about 85%. So that's why we can see that the nanostructure is most important to enhance the surface area or to enhance the efficiency of any material, any device as well. And after that we can see that if we use the nanomaterials in the nanoparticles way, if we use the nanoparticles, the electron injection process is very slow, as the electron have to face so many hurdles to injection for the injection process. So that's why we are optimizing this nanostructure by utilizing the other nanotubes, and the nanotubes have the fast electron transport due to the direct injection process. And we can see here in this way the electron is have the so many hurdles, and in this way if we use the nanotubes, electron having the straight path for the injection. So that's why we are optimizing this nanostructure, and we can fabricate these nanotubes by utilizing the very well-known technique, electrochemical anodization process. And in the electrochemical anodization process, we can use the electrolyte as ethylene glycol and ammonium fluoride and the Di water-based electrolyte. And in this way, we get this one is the counter electrode, and this one is the cathode anode, and these all are the parameters of the anodization parameter. And in this way we can further optimize the nanostructure. The first one is the parameter is the anodization time, second one is the anodization temperature, Di water concentration, anodization voltage, pH value, and the nature of the counter electrode, and the seventh one, the distance between these two electrodes. So in this way we can optimize the nanostructure by utilizing these all anodization parameters and by changing all these parameters. So in this way, after that, when we achieve the nanotubes, we can transfer these nanotubes onto the FTO glass for the front side illumination mode of the dye sensitized solar cell. So in this way we can see that anodization Ti foil emerges in H2O2 solution, and after that anodized titanium nanotubes can be detached from the titanium foil, and after that we can transfer it onto the FTO glass for the front side illumination mode. And by using the electrolyte for the sticky purpose. And after that the annealing process is also very important, as we know that titanium structure has the three phases. The one is the anatase, and the other one is the brookite, and the third one is the rutile. And the most convenient and the feasible structure is the anatase phase, that can be achieved up to the 400 degrees centigrade. And in this way we can see that in this way this amorphous nanostructural amorphous titania having is not having the straight path for the injection of electron. And also anatase and the rutile phase, if we have the hybrid phase, is also not for so feasible, and the anatase titania is very suitable for the injection of electron, and the less grain boundaries if we annealed at 400 degrees centigrade. And these are the some images of titanium nanotubes if we use in 4 hours, 6 hours, and before annealing it's first the phase of this nanotubes, and this is the bottom view of the nanotubes. And after that we can see that in this diagram, this is the schematic diagram of the dye sensitized solar cell, and we can see here these are all are the nanotubes and dyes uploaded on the nanotubes, and these all nanotubes are transferred onto the FTO glass. This part is acting as a photoanode, and the other part is acting as a counter electrode, and this part is a FTO base platinum, and this is the iodide electrolyte, and the light is entering from the photoanode. As we are using FTO glass, this is the due to the transparent mode of the dye-sensitive solar cell, the light is entering from this side. And another factor is also very important is the roughness factor. Is calculated by this formula, and in this formula we can see there D is the diameter and the W is the width of the nanotubes. So we can enhance the efficiency and roughness factor of the nanotubes by utilizing by changing the diameter of tubes. So in this way we have, if we use the nanotubes with anodization of 4 hours, we have achieved the efficiency of 2.01%, and after that if we use the nanotubes with 6 hour anodization, we have achieved the efficiency of 3.12%. so we can further enhance the efficiency of dye sensitized solar cell by optimizing the nanostructure of titanium. So another part of the nanohexagon arrays. Nanohexagon array is the modified structure of nanotubes. So in this nanotubes we have changed the parameter of nanotubes. In this way we have anodization time of 8 hours and the temperature of 5 degrees centigrade, and the lower concentration of DI water, and the voltage of optimum voltage of 50 volt, and the pH value of about 5.5, and the similar counter electrode as titanium foil, and the distance between an electrode is the 1.5 centimeter. And in this way we can achieve the nanohexagon structure. In this nanohexagon structure we can see these two processes are taking place at a time. Anodization speed, that is called V electro, and the chemical etching speed V displacement. So that's why first of all we will get the freestanding TiO2 nanotubes, and after that we will get the nanoporous nanotubes, and if we change the further parameter, we can achieve the nanohexagon arrays. In this way we can see from the same images the nanohexagon structure is clear, and this nanoporous nanohexagon structure is due to the coordination number of 6, and these porous nanotubes is transferred to the nanohexagons, and we can see here this structure is similar to hexagon, so that's why we may call it the nanohexagon. And this structure has the higher surface area to maximize the dye uploading and for the enhancement of the efficiency. And after that we can further enhance the efficiency of titanium nanohexagon by utilizing the titanium tetrachloride treatments. And in this way we can see if we deposited the TiO2 nanoparticles on the nanohexagons, so we can see this is the same images of the nanohexagon with the TiCl4 treatment, and this is the EDS image of TiCl4 treatment, and in this way we can see Ti and oxygen is clear from the EDS analysis, and the XRD pattern is also clear we can see their anatase phase is very clear, and is matched from the PCD KPDF card number 211272, and anatase structure is most important for the injection of electron. And the IV characteristics and the absorption spectra of the nanohexagon arrays is also shown in the figure. We can see there nanotubes having the lower efficiency, and after that, if we use the nanohexagon, efficiency is enhanced. If we want to further enhance the efficiency of dye-sensitized solar cell, we may use the nanohexagon with the nanoparticle, and we may achieve the efficiency of dye-sensitized solar cell is the very high, and IPC is also very high, which is compatible with the IV measurements. And absorption spectra of the nanotubes and nanohexagon and the nanohexagon with the nanoparticles is also clear that the absorption is very high by utilizing the nanoparticles with the nanohexagon. And this is the photovoltaic parameters of nanotubes, nanohexagon, and the nanohexagon with the nanoparticles. And in this graph, we can see there in this table, ADA is the amount of dye absorption, and the S is the evaluated inner surface area for the dye absorption. So we can see there, we can see here the dye absorption is very high, and the dye and the surface area is also very higher by utilizing the nanohexagon with the nanoparticles. And after that, to see the effect of anodization parameter on the nanostructure, we use another parameter for the anodization. If we use the temperature of 15 degrees centigrade with the anodization time of 2 hours and the DI concentration of 3 volume percent, we may, and with the voltage of 50 volt, we may get the TiO2 nanopores. And after that, if we change the temperature of 10 degrees centigrade and the anodization of 4 hours, DI water concentration of 2 volume percent, we got the titanium nanotubes. And after that, if we further change the temperature, anodization time, DI water, we got the TiO2 nanohexagon arrays. And after that, with the temperature of 0 centigrade, we got the nanonet. And after that, with the minus 3 degree centigrade, we got the nanostructure of titanium as a nanograph. So we got the 5 nanostructure as nanopores, nanotubes, nanohexagon, nanonet, and the nanographs. And these all are the cross-sectional images of the nanohexagon, nanonet, nanopores, and the nanotubes. These all images are clear and elaborate the same images in terms of nanohexagon, nanonet, and the nanopores. And after that, the structure and the photovoltaic parameter of these 4 nanostructure is shown in the figure. We can see here all the phases of the titanium are anatase, and in the nanohexagon, nanonet, and the nanopores, we can see there these efficiency and the IPC of the all devices are shown in the figure. And the nanohexagon having the higher efficiency of 5.29% with the absorption of dye absorption of 6.7 into 10 is power minus 6, and the surface area for dye absorption is the 871 centimeter square. So in this way, the nanohexagon structure is the most optimized and the most convenient structure to enhance the surface area and for the uploading of dye. And after that, we may enhance the surface area by utilizing the TiCl4 treatments. And we can see there, if we use the 0.2 molar concentration, the same images is as under. If we enhance the surface, if we enhance the concentration as 0.3 molar and 0.4 molar, we can see all the nanotubes are blocked by using the higher concentration. And after that, EDX analysis is also shown, and these all are the IPC and current density is also shown in the figure. And in this photovoltaic parameters, we can see there titanium nanohexagon with the treatment of 0.2 molar titanium tetrachloride. We can see the PC of 6.64% is achieved with the dye absorption of 8.9 into 10 to the power minus 5 per mole centimeter square. So in this way, the lower concentration is better, as when we use the higher concentration, the all nanohexagon is blocked. So that's why we cannot upload the maximum dye, and in this way the efficiency is decreased. So this is the TSCL for treatment with the open circuit voltage and with the JSC, current density, fill factor, and the power conversion efficiency. And after that, we can further optimize the photoanode or the dye sensitized solar cell by utilizing the other nanomaterials with the heterojunction like zinc oxide and the titanium nanohexagon arrays based heterojection. So we can use the fissile immersion method for the zinc oxide based nanohexagon arrays, and we can see the same images of zinc oxide and TiO2 nanohexagon array based heterojunction, and these are all the same images with the different concentration of 0.2 molar with the 30 minutes and the 0.4 molar and the time is 60 minutes, and 0.6 molar with the time of 90 minutes and 0.2 molar with the 30 minutes. And we can see here that this concentration is very convenient for the to lower the recombination rate, as the zinc oxide is acting as a barrier for the recombination. And in this EDS graph, we can see the zinc oxide and the titanium, and we can see in the graph the zinc oxide, the elemental composition of the zinc oxide is clear, and also the XRD line pattern is also clear. A for anatase and the H for hexagonal zinc oxide, and C is the cassiterite tin oxide. In this crystalline structure, we can got the crystalline cassiterite tin oxide, as all the samples are transferred on to the FTO class. So that's why we got this pattern. And IV characteristics of zinc oxide titanium based nanohexagon arrays, we can see here the photovoltaic parameter of the zinc oxide based 0.2 molar with the lower immersing time having the higher efficiency of 6.85%. So that's why the lower concentration is far better as compared to the higher concentration, and the lower immersing time is also very important. So that's why if we increase the immersing time and increase the concentration, so all the nanohexagon will be blocked. So that's why the lower concentration is much more better than the higher concentration. And after that, the graphical representation of the graph, all the photovoltaic parameters are shown in figure. So we can see here the open circuit voltage with the effect of JSC, fill factor, and the power conversion efficiency with the immersing time. And after that, electrochemical impedance spectroscopy is also can be characterized with the help of impedance spectroscopic measurements. So in this way, we can see that the 0.2 molar concentration with the immersing time is also very higher efficiency in terms of the collecting rate, and the all the other parameter like resistance and the time, and the lifetime of electron. So that's why the zinc oxide concentration and the zinc oxide heterojunction is very important for the lower recombination rate. And after that, the band and the schematic diagram of the zinc oxide based dye sensitized solar cell is shown in the figure. We can see is also the modified structure of the dye sensitized solar cell. In this way, we have designed the nanohexagon with the zinc oxide and also the dye. And in this way, we can see nanohexagon is shown in the figure, and the zinc oxide with the blue color, and the dye with the other color. So in this way, we got this advanced form of the dye sensitized solar cell by utilizing the zinc oxide nanohexagon based photoanode. And in this way, we can see by utilizing the zinc oxide, the recombination rate could be minimized, and we got the higher efficiency. And after that, to increase the further efficiency of the dye sensitized solar cell, we have further modified the photoanode with the tin oxide based photoanode. And this is the structure of the tin oxide and the titanium nanohexagon array based heterojunction. And these all the same images with the concentration, and also emerging time is the same in all these concentration. And these are all the same images of other concentration: 0.25 molar with the time of 30 minutes, 0.50 molar with the time of 30 minutes, and the 0.75 in the 0.25 is the another is the cross sectional area of the samples. XRD and the IV measurements of the tin oxide based photoanode is shown in the figure. We can see here all the XRD pattern is belong to titanium, and also with the tin oxide KGC periods card 1445 showing the tin oxide crystalline plane. And also that we can see the efficiency of the tin oxide based solar cell having the efficiency of 6.34% is almost similar to the zinc oxide based solar cell. So in this way, the concentration of 0.25 molar and the time of 30 minutes is most feasible for the fabrication of tin oxide heterojunction based solar cells. And these all are our publication regarding solar cell. In this way, we can see here in this way investigation of the surface modification of the titanium nanohexagon array based photoanode with the tin oxide nanoparticle for highly efficient dye solar cell. And also another publication in by changing the counter electrode RGO and iron oxide base counter electrode with the replacement of platinum, as the platinum is very expensive. So that's why we have replaced that. And also we have introduced the plasmonic dye sensitized solar cell by utilizing the metal nanoparticles like thorium, Ag, and the copper with the phenomena of surface plasma resonance. So in this way, we have introduced the AgRGO titanium based ternary nanocomposite based photoanode for the further enhancement of the efficiency of the dye sensitized solar cell. And in another paper, we have replaced Ag with the copper, as the copper is very cheap as compared to the Ag. So after that, in another paper, we have replaced the copper titanium with the RGO based photoanode. And after that, the Ag, RGO and titanium nanocomposite based photoanode having the same images as shown in figure. We can see the same images of all these nanostructure, and the EDX analysis is also confirmed the elemental composition of Ag, Ti and And after that, the XRD pattern of the AgRgO titanium based nano composite and TGA thermograph is also shown to confirm the stability of dye-sensitized solar cell with the temperature of up to 300 degrees centigrade. And after that, the copper titanium based nano composite is also can be seen by these same images, and the elemental composition is also can be confirmed by the EDX spectrum and XRD pattern of the copper titania. In this way, we can see here the titania having the structure of a rutile, and the copper titania having the TGA analysis with the stability of only 2.5% weight loss at the 800 degree centigrade, and after that the absorbance is also very clear. We can see the visible range, all the absorption is in the visible range. And in the last part, we have replaced the counter electrode with the RGO and iron oxide based nano composite. So iron oxide nano composite based counter electrode is very cheap as compared to platinum based counter electrode. So in this way, we can see the same images of the RGO iron oxide based nano composite, and these EDX spectrum is also can be seen here, and XRD spectra, absorbance and TGA graph is also confirm the elemental composition, crystallinity, and also TGA thermograph of the RGO iron oxide based nano composite. And the IV measurements, we can see the photovoltaic parameter of the titanium with the platinum based counter electrode having the efficiency of 3.13%, and the titanium with the RGO iron oxide based composite having the efficiency of 1.28%. And after that, we have copper titanium with the platinum having the efficiency of 3.89%, and copper titanium with RGO and iron oxide having the efficiency of 2.20%, and the most higher efficiency of AgRgO titanium based nano composite having the efficiency of 6.8% with the IPC of 68%. So in this way, AgRgO ternary nano composite based plasmonic solar cell have the higher efficiency of 6.87%. So these in the last we have the conclusions. We have successfully synthesized 5 nanostructures like nanopore, nanotube, nanohexagon, nanonet, and the nanograss, and the dye sensitized solar cell based on the titanium nanohexagon arrays with the 0.2 molar titanium treatments have the power conversion efficiency of 6.64%, and the lower recombination rate has been observed by utilizing the zinc oxide titanium based nanohexagon arrays. And after that, synthesized AgRgO titanium and copper titanium based hybrid nanocomposite by different approaches. Synthesized hybrid RGO iron oxide based counter electrode by fissile wet synthesis approaches, and the higher efficiency of AgRgO titanium based photoanode demonstrated a higher power per conversion efficiency of 6.87%. And I acknowledge that this research work was fully supported by the Higher Education Commission of Pakistan under NRPPU grant, and authors are also thankful to UF, XJTU, and experiment and the characterization, and it's not to our research students. And after that, we have one PhD position in our research project, and we need one PhD student. So if someone from our country is interested to join our group in terms of as a PhD student, so he or she can avail this opportunity. So the last, thank you very much for your kind attention. If you have any question, you may ask any question.
Thank you very much, Dr. Saab, for your great presentation, and I would like to extend thanks from my institute, and you also gave us a very great opportunity to join your group. If somebody is interested, he or she welcome to join you. And now I would like to take any question from somebody. If someone have a question from Dr. Saab, you can ask. Okay, one question. My question: how to do optimization from Adnan? Sir, I have get one question from the Adnan Saab.
How to do the optimization?
Yes.
Actually, optimization is if we got the optimized, it means that we can see the optimized way if we use the different concentration, say 0.1 molar, 0.2 molar, 0.3 molar, and we got the efficiency and we got the higher efficiency at the 0.1 molar, so we can say the 0.1 molar is the optimized concentration for this device. It means such state we can at the higher efficiency. So in this way we can see the optimized way, optimized concentration, or optimized nanomaterials. So I think is the meaning of optimized. So we can use in the different way, in the optimized concentration, optimized temperature, optimized nanomaterials, and etc.
Thank you very much, sir, for your time. Again, I'm really very grateful to you, and even I am very grateful to your opportunity. I love to join your group if I extend the other body can join you, and that's very great news for all of us. Okay, whether join your group. Thank you, sir. Thank you very much once again from our
Okay,
side.
thank you very much. Okay, welcome. Thank you very much.
Okay, now we have another outstanding professor from the University of Karachi, Professor Dr. Bushra Ahmed Khuram. She is an assistant professor from the Department of English. Now I would like to invite you, Professor Bushra Ahmed Khuram Saiba, to give. I want to give you my stage to please. Over to you, Professor Saiba. Over to you this session. अपनी mic मैम on कर दीजिए. अपनी mic.
Okay, it's on now. Can you hear me?
Yes, ma'am. And thank you very much. Thank you very much, ma'am, for your time and attention.
Thank you very much for inviting. It's a pleasure to be here. Let me just share my screen so that I can start my presentation.
अभी मेरे ख्याल में किसी की screen जो है.
Okay. Somebody's screen is open. Okay. Let me see. And just please, Sajid, let me know if you could see my screen now. Could you see my screen?
Yes, ma'am.
Okay, wonderful. Thank you so much. Okay, Assalamu alaikum, everybody. It's truly a pleasure to be here and to talk about reading, which is very, very close to my heart. And I think it's not only close to my heart, it's close to all education systems around the world. Because no matter which subject you are teaching, whether you're teaching science or art humanities, all subjects in social sciences, you can't bypass reading. All students, it's been said, and as well as all teachers are called teachers of reading. Despite the fact that you are teaching whatever subject, you are a teacher of reading as well, and you read yourself a lot. And therefore, it is extremely, extremely important how we can read effectively ourselves and how we can enable our students to read effectively. Having said that, I'll just share with you the fact that the recent decades have seen extensive research on reading. Reading in the 21st century has been at the top of the list in terms of research literature that has been carried out. And the reason obviously is pretty simple. We all know this is a knowledge-based economy, and in this knowledge-based world, reading is considered critical to academic, economic, and social success. And we don't have to go very far to see how important reading is for success. We know from research, from the interviews by extremely successful entrepreneurs, from those who have left their mark in the world, who have brought a change in the system, these people are, among other things, voracious readers, which means they are avid readers. They read a lot. And let's have a look at some examples. We all know who Bill Gates is, don't we? Bill Gates very proudly says that he reads one book per week. And by reading, basically, obviously, he means he understands this, he has a critical dialogue with it, and so on, as we will see later. So he reads one book a week, although he is extremely rich. If you think about reading, many people study, get degrees because they want to earn a living. The people right in front of you, they don't need that kind of hard work to earn their living. They are already extremely ultra-rich people, but still they give so much importance to reading. And maybe that's one of the reasons why they are where they are. Mark Zuckerberg, we all know who made the Facebook, reads one book every 2 weeks. Elon Musk is an avid reader. He reads so much that he has said in a recent interview that he has started, because he travels a lot, you know, he is a physicist, he is developing space cars and so on, that he has now recently started reading even on his mobile because he's traveling and having so many meetings around the world. Warren Buffett, one of the richest men on this planet, spends about 80% of his day reading. And Oprah Winfrey, quite a name, we know reads one book every month. And these are basically books that they are talking about. This doesn't even include the articles, the magazines, and etc. that they read. So you can see these people are immersed in reading. And once again, I'll repeat myself by saying that this is what perhaps has led them, among other things, among hard work and so on, towards success. But why books are so important? Why entrepreneurs around the world or any successful individual read so much? Because we know from literature, that reading is the best way of vicariously learning. If you are not somewhere, you can learn about that invention, you can learn about that development by reading what has been written about this. We know that books can be a source of inspiration. They develop skills and provide tips and business strategies. They give us tips and ideas about what could be done or what has been done before, and therefore where's the gap which we can jump in and fill in terms of creativity. Reading can provide multiple perspectives and can help us join the dots and do things in a way that has never been done before, because there are different dots which are interconnected. But when you read, you kind of join them by understanding what has happened before, how people look at different things, and how new things could be done. We also know books can help us learn from the success and failures of other entrepreneurs. And I'm stressing entrepreneurs here because in this time and age, many people are talking about starting your own business. This is where the entire world is moving towards, especially at the higher education level. But obviously, you can learn about success and failures even if you don't want to be an entrepreneur, if you just want to be successful in your field. And we know Isaac Newton, whom we all consider as a giant, he has said something very remarkable and deep. He has said, if I have seen further than others, it is by standing upon the shoulder of giants. So he has not claimed that he has been successful out of his own effort and he never needed anyone. He stood on the shoulder of giants, people before him, to be able to see further ahead. And obviously, how would you stand on the shoulder of giants? By reading their work, by going across their work. And at his times, obviously, we know one of the only means of learning what has happened before, because there wasn't a YouTube, there wasn't an internet, was through reading. So you cannot really bypass reading in any age, and not even in this age. Now, if reading is that important, and if that's what brings success, then how can we enable ourselves, and I'm addressing ourselves here as well as our students, to become effective readers, which is the title of my talk. And the answer is, like everything else, when you want to do something productive, something useful, something creative, you lay the foundation. And you and I and we as people and as teachers of different subjects need to lay foundations for ourselves to become effective readers, and for our students to become effective readers. And how could that be done? And this is what this talk is about. It's going to share with you some ways of enabling our own selves first, and then our students to become good readers, or what we call strategic readers. Let me at this point in time, let me share with you that while I was doing my PhD in the area of reading from the University of Warwick in UK around 4 years ago, I was invited by University of Warwick itself to train their BA, MA, MPhil, PhD and postdoc students on how to read, because this was an area of my expertise and this was where my heart was, and therefore I shared with them ways of improving their reading skills, which really helped students. So I hope this is going to be helpful for you as well and for your students. Also, I was invited at that point in time by Regent University London, by University of Manchester and Leeds and other universities in UK to talk to their teachers on how reading could be taught to the students. So what I'm going to share with you are tried and tested techniques, not only in Pakistan, but in the UK and other places as well. So I hope that's going to be useful for you. And while you're listening to this, try to think about how you could take it back to your system, to your own students, and how could you yourselves become a better reader as a teacher, as an individual, because obviously we can teach another something that we ourselves know. If I don't know how to drive, I can't teach anyone how to drive. So if I'm not a good reader myself, I obviously can't teach others how to become a good reader. Okay, having said that, let's move on. So the ways of improving or becoming a strategic reader as defined by research is to promote reading strategies in learners and to promote metacognition in learners. And we will see in a minute what these terms entail, what is meant by these terms. You might have come across these or you might have not. But reading research indicates that all good readers are basically strategic readers. So readers need to be strategic readers to become successful or good readers. And this is what, and the importance of being strategic readers also is being shown by literature. Research indicates that there is a strong interface between one's ability to read strategically and one's ability to excel academically. So it's directly proportional. If you can read strategically, which means if you know how to read, what are your strategies? And we will unpack that word inshallah soon, you will excel academically. So there's no shortcut to reading. There's no other way to excel academically if you don't read strategically. And the good news is that the research also tells us that students could be helped to become effective readers by understanding how to use reading strategies to aid comprehension. And this begs the question, what are reading strategies? Okay, so reading strategies basically in the literature is basically defined as comprehension strategies. That means strategies that help learners comprehend the upcoming text. So in other words, as you can see on the screen, reading strategies are the comprehension processes that readers use in order to decode text. That means to understand what is written, to understand the words, and to construct meaning of text. Constructing meaning means basically making sense of what is written in the text. So reading strategies are also defined as a deliberate action, an action that readers take by choice, deliberately. that readers take voluntarily, which means, in other words, you can't really force anyone to use reading strategies to develop an understanding of what they read. So to briefly highlight the keywords, it's deliberate, it's voluntary, and obviously it's going to be hard work. It's not going to be very simple and easy. It's also defined as the mental operations, what's happening in the mind of the readers, whether they are students or teachers. These are the mental operations which involved when readers purposefully, that means once again deliberately and having a purpose, approach the text to make sense of what they read. These may be either conscious techniques or unconscious processes applied automatically. And as I'm going to share some strategies, you will say that, oh, I do use them, because you have perhaps through your reading have unconsciously picked up those cognitive processes, or maybe somebody has taught them to you consciously, which is not the case really in Pakistan and even abroad. But it is possible that somebody has taught you consciously, or you have picked up simply by reading. So why use strategies? If you try to sum it up, all good readers use strategies because they help you elaborate, organize, and evaluate information in text. And strategies help a reader take control of their own learning. So if I try to sum up what reading strategies are after having introduced you so much to it, I would say reading strategies are deliberate, as I showed you earlier, that you use it deliberately by choice. These are effortful, which means don't assume that it's going to be very easy to apply reading strategies to a text. It's not going to be hugely difficult, but it would require some effort and hard work on the part of the reader. It's goal directed. You always try to achieve something, and therefore you use that a reading strategy to achieve that goal. So it's always goal directed. We'll skip the last point, it's a bit technical. So which means if you're planning to use reading strategies yourself or asking students to use it, the students need to be willing to use it, or you yourself need to be willing to use it, and you yourself are willing to put an effort to become good reader and to use reading strategies, because good readers, it's being said, possess a variety of strategies for accomplishing the challenges and goals that face them. And they're also motivated to employ strategies and attribute their success to the use of strategies. And also, good readers are able to understand what strategy is appropriate for what purpose. I also use the term called metacognition. I understand it's getting a bit dense because there's so many concepts I'm throwing right now, but it's important to understand that the term metacognition means, you might have heard about it, it basically in layman terms means thinking about thinking, okay? Which means you think about what you're thinking. And in terms of reading, readers basically think about what reading strategies they are using to understand the text. And all good readers, all effective readers are metacognitively aware of their cognitive processes, which means they understand what they are doing while reading, even if it is not at the conscious level. If somebody asks them, how did you arrive at the right answer? They will be able to point out a cognitive process by obviously reflecting and thinking a bit, and say, I did this to be able to understand the text. Okay. Now, I would really encourage, I'm not really sure if you can write in the chat box, but I would really encourage few responses on this question in the chat box, so that I understand where you are coming from and what's your understanding of reading strategy or reading. Is it possible for you to list a few reading strategies in the chat box? Is it enabled? Sajid, could participants write? Oh, it's available. It's available only to team members, Sajid? Or could participants write in the chat box? We can't hear you. I think you need to unmute yourself.
मैम ये आपकी स्लाइड्स वो हो गई
अच्छा नहीं वो तो मैंने अभी की है. The question is, could the participants write in the chat box right now, or could they not? If not, that's okay. We'll move on.
Okay, skimming, scanning, and intensive reading. Mohammed Hassan Sahib.
Oh, okay. He's saying skimming, scanning, and intensive reading. Okay, wonderful. Okay, any other strategies? And we will discuss these for those who have not who don't have an understanding of. Any other strategies that somebody could list down? I think Sajid, you could read that. I can't for some reason.
Okay, we are taking. I will show you ours. Say here.
Okay, thank you.
Word association.
Word association, brilliant, absolutely. Okay, any other strategy that comes to your mind? And I don't want a Nobel Prize winning definitions or list. Just write down whatever comes to your mind. Okay, Sajid, any other?
Okay, identity, the main idea, and the summarization.
Excellent, absolutely. Identifying the main idea. Yes. Any other?
Predicting, visualizing, questioning, detailing, oral, and identifying them.
Identifying, visualizing, predicting, questioning. Brilliant. Absolutely. These are very important reading strategies.
It's from the Bilal Roger.
Okay. I think that's so far so good. And that's quite a comprehensive.
Extensive reading and story maps.
Okay. But these are techniques. Basically, extensive reading is a kind of reading. We have two kinds of reading: intensive reading and extensive reading. Just for a second, I'll just give this info that extensive reading basically is reading for pleasure purposes, for reading, not for academic purposes. Intensive reading basically is for academic purposes, where you want to understand each and every detail. But when you read a novel, when you read a play, when you read a poem, you don't care about whether you know all the details, because you're reading extensively, and that's the purpose. Okay, and reading strategies, reading process itself is divided into three components. The first is before reading, then during reading, and then after reading. So what I'm going to do right now, before they have started reading. And I have asked this question from a number of people because I do teacher training sessions for Higher Education Commission Pakistan and for British Council Pakistan as well. And many times I have asked faculty members around Pakistan when I go to Islamabad or when I visit their universities, and nowadays online, what is it that they do before reading? And sometimes some of them give answers which are linked with reading strategies. Other times they share with me that they make a cup of tea, they take out a stroll and so on, which is fine, which is okay, because they are kind of preparing themselves mentally for upcoming reading, or they sit at a place which is well lit and well aired, because you need fresh oxygen to keep your mind fresh, and all that is fine. But
आपकी slide जो है वो move नहीं हो रही slide.
जी मैंने भी move की नहीं है.
अच्छा, okay, that's fine.
जी मैंने भी की नहीं है. I'm just building up the background. Thank you, Sajid. Okay, so these are some of the things that good readers also do. Yes, they set up their background so that they are sitting at a place which is very well lit, so that your mind doesn't feel like sleeping. And they make sure that, for instance, they're not sitting on a bed while reading, because we, as you all would definitely know, you are from sciences background, there is the term called psychological pathways, which means in our minds, neurons interact and make psychological pathways, connecting links between one neuron and the other, which basically builds our habits. So if you try to sit on a bed and read, your mind would tell you, and you wouldn't even get to know that this is a place to sleep. And therefore, very slowly, gradually, you will keep slipping in your bed, and you might sleep. जिसे वो जोक में कहा जाता है ना कि किताब थोड़ी देर बाद नीचे होती है और आप किताब के ऊपर होते हैं. तो उसकी वजह ये है कि हमारे माइंड में जो साइकोलॉजिकल पाथवेज हैं, वो हमें ये कहते हैं कि तो बिस्तर पे आप आ गए ना, तो सोने की जगह है. But it could happen the other way. If you read too much in bed, for instance, your mind will start telling you next time you will go to bed that not to sleep, because this is a place where you read. So it's very, very dangerous to mix up your mind and to confuse your mind that much. And therefore, it's extremely important to make sure that you're sitting at a place where you just read. बाहर जब मैं वॉरिक में पढ़ रही थी तो हमें ये भी बताया जाता था वर्कशॉप्स में कि आप अगर वो लैपटॉप जिस पे आप पीएचडी का काम कर रहे हैं, डोंट एवर चेक फेसबुक ऑन इट, डोंट एवर चेक लिंक्डइन ऑन इट, डोंट एवर वॉच अ मूवी ऑन इट, because next time when you will sit on that laptop and when you're doing something difficult, your mind will distract you and will say, okay, check Facebook for 5 minutes, just 5 minutes, and then that might eat up in an entire hour. So setting up your mind basically for reading, preparing your reading is important. But what I'm talking about here are called metacognitive behaviors of good and poor readers, which means what exactly good and poor readers do before reading.
We also get some response from our audience. Amna Baloch, visualizing and relating, and from the inductive and deductive methods, fast reading from the Majid.
Okay, thank you so much, Shazid, for sharing. Absolutely. So these are different. Some of them are techniques. Some of them are methods. What we are sharing here are strategies. Okay, there are difference between strategies because, as I said, strategies are cognitive processes. What happens in the mind up here, which is obviously not very visible. You can't really see what is in your black box. Okay, you can't really open your mind and say, oh, this is what I do. But through processes like think aloud protocols and other methods, we are beginning to see what actually good readers do while they read. And that's what I'm trying to share here. So as you can see in front of you on the screen, there are two columns basically. One lists the good or mature readers' behavior or strategies, in other words, that they use before reading, and the other column lists poor or immature readers' behavior or strategies while they read. So let's go through them one by one. The very first thing that not the very first thing, but one of the things that good or mature readers do is to activate their prior knowledge. Initially, if you are not a very effective reader, then you consciously apply this strategy. Good readers automatically do it without even being aware of the fact that they are activating their prior knowledge. What does that mean? Prior knowledge basically means background knowledge. Activation, we all understand. So, which means they tap, they question, they bring to the surface what is it that they already know about a topic even before they start reading. And why they do it? For several reasons. Because this basically makes them realize what is it that they know and what they don't know. Also, this builds their interest in what they're going to read, because then they begin to think, oh, I want to know more about this particular area because I have very surface level understanding of it. Also, it keeps them alert during reading because they can link with what they have thought about with what they are reading. So it's extremely important reading strategies, and readers are advised, those who are not very effective readers are advised to activate their prior knowledge. Let me also share with you, how do you define effective readers? Obviously, effective readers are the ones who understand what is written in the text. What is it that the author is trying to communicate to you? But they are also critical about it. They do not only accept it at face value because the authors have written this. The question is, they challenge it. And they do read it at a reasonable speed, and sometimes very fast speed. You might be a bit surprised to know that good readers can read at the speed of 1500 words per minute. 1500 words per minute. You might know J.F. Kennedy, the American president who was assassinated. His reading speed was 1500 words per minute. And when I talk about reading, it means always with understanding, always with comprehension, never without understanding or comprehension. So people are able to read, and all American presidents have always read not below 1000 words per minute reading speed. And therefore it's being said readers are leaders in the world. We know this very well, this axiom, that readers are leaders. But obviously for that you need to be a good reader. If you really want to be a leader in your field, you need to be a very good reader as well. So what is it that good readers do? Coming back to that, they obviously read at an appropriate speed. Sometimes they should be able to read at the speed of 1000 or 1500 words per minute. And if they're learning to be good readers, then they need to learn how to apply these reading strategies so that they begin to read at that reading speed. Okay, so good readers activate prior knowledge. Poor readers, no prizes for guessing, start reading without preparation. which means they do not activate their prior knowledge. They just pick up a text, look at the first line, start reading from first line, and then go on to the last line without wondering about what is it that they already know. Why is it important to know what you already know? Because another definition of reading is that reading is forming a bridge between what is known and what is unknown. In other words, all readers make a bridge between what they already knew and what they are learning. So if they do not tap what they already know, if they do not bring it to the conscious level, they will not be able to build this bridge between what they already know and what they're learning. Okay? So that's why good readers activate their prior knowledge so that they can actively formulate this bridge between what is known and what is unknown. On the other hand, poor readers start reading without preparation. Other than before activating prior knowledge, good readers also predict. It's not written here, but let me elaborate on this. They predict what the text will be all about. For instance, if they are given a text called Metacognitive Behaviors of Good and Poor Readers, they will try to look at the title and try to actively guess. Prediction means guess. They will try to guess what this text is going to be about. So they might say, oh, it's going to list down some behaviors of good readers and poor readers. Metacognitive, maybe it's going to talk about cognition, which is thinking. Even if you don't know the word metacognitive, you will think about what the text is going to be about. Poor readers obviously don't do that. Okay. Good readers, on the other hand, also understand the task and set purpose. And poor readers, they know they have to read, obviously, because they are given a text, especially academic text, but they read without knowing why they are reading it. In other words, let me give you an example to understand this, because this is a bit technical. Understand task and set purpose, which means they understand what exactly they're going to get out from the text, why they're reading it, because we know that not all texts are to be digested. Some are to be chewed, some are to be tasted, some have to be some have to be digested and some have to be just thrown away because you don't find it appropriate for your own purpose. So this is what they understand, why they are reading what they are reading, what exactly they want to draw out of it. For instance, if I ask you to, if I give you a 2-pager text, and if I ask
Ma'am, hello.
Okay, I think you muted me by mistake. Okay, did you hear what I said about giving a gist? Was I audible then? Sajid, if you could tell me where you lost me. Okay, let me just say it again, just to save time. So if I, for instance, ask you to give me the gist of a 2-pager text, then if you're going to read each and every line, then that's not going to be an appropriate strategy for it, because you're just required to give me a gist, an overall idea of what this text is about. And therefore, the best strategy is going to be skimming. Just skim the text and give me the overall idea what this text is all about. Okay, so it's important to understand the task and set the purpose for reading according to that task. Okay, and good readers also choose appropriate strategies, while on the other hand, poor readers read without consideration how to approach that material. Now we have 15 more minutes, so I'm going to just list through some reading strategies. Reading strategies are categorized at 2 levels. One is called local strategies and the other is called global strategies. Since you are not teaching TESOL, I'm not going to share the definition of these, but I'm going to share with you the strategies which comes under local strategies and the strategies which comes under global strategies. Now, local strategies deals at the level of words, basically phrases or sentences. And some of the local strategies are, some of you have also mentioned them, paying attention to the key words in the text. which basically means knowing what are the most important words in the text and paying attention to it so that you comprehend it. Which in other words also means not all words which are written in the text that you have are important or should be given equal importance. No, one of the problems with our education system is we tell our students to know the words of each and every word which is in the text that they are reading, which is mis-teaching them how to read, because there's a vocabulary which is relevant to the topic of the text and there's a vocabulary which is irrelevant. So you don't have to stress on understanding all the words, but understanding an overall understanding of what this text is all about and what are the key words in the text. Second is paying attention to thesis statement, which is the main idea of the text. Thesis statement or the main idea basically is in majority of the text, in around 90% of the text, is in the first sentence of the text. Okay, not the first line, the first sentence, which contains what we call the core idea, the main idea, or the thesis statement. And therefore, while you are asked to do skimming, you are asked to read the first sentence of each paragraph very quickly so that you can understand the main idea of the text. Okay, so and that's what good readers do. They do not read the entire paragraphs very carefully. They try to pay attention to the main idea, which is usually the first sentence in the paragraph, because the rest of the paragraph then are examples or elaboration of the main idea. But in some texts, the main idea is also in the middle, and in others, it could be at the last sentence of the paragraph. But mostly it is at the start of it. Another strategy that good readers use, and I'm sure we all use it a lot, which is called a fix-up strategy. You use this strategy, you fix up comprehension problems. Fixing up, we all know, we fix up a car when it stops working. We fix up anything which stops working. So rereading is a fix-up strategy that good readers use. Whereas the other strategy that good readers use is called using context. Now, it's important to understand what does that mean. It basically means in all texts that we are reading, there's a text that goes before a difficult word or a phrase that you have come around, or after a difficult word or phrase that you have come across. Okay, what good readers do, they do not immediately run to the dictionary to understand the meaning of a word, because that can stop the reading process, that can disrupt the reading process and can stop you from understanding it effectively. What good readers do is they try to use this context, which is also called core text, the text that goes together with other words, and try to understand the meaning of the word they could not understand by reading the core text, the context, carefully and again and again. Okay, because if you will open the dictionary, which is what our education system generally teaches us, for each word, if you're going to open the dictionary, and if there are 5 words on a page that you have come across which are difficult, you can imagine you are stopping your reading process 5 times on a page, and by the end of the page you might know the meaning of 5 words, but you will not really remember what is it that the reader was saying. And therefore it is highly discouraged in current times and age to not to look up the dictionary until unless it's extremely important to do so. So try to use the context to guess the meaning of the word, and that's what the next strategy is linked with, guessing. You guess the meaning of the words, the phrases, and sometimes good readers just skip it. If they can't understand the meaning of a word or a phrase, they just skip it, move ahead, because sometimes the text which is coming next helps you understand what you have not understood before. So it's important to understand that you need to guess and skip at the same time. You don't have to read and understand each and every word. And I'm emphasizing this a lot because majority of our students suffer from this wrong misteaching, the faulty reading that you need to understand each and every word to be able to comprehend the text, which is not true. Another local strategy that good readers use is recognizing and commenting on text structure, text genre, and writing style, which basically means on commenting on whether this is a well-written text according to its purpose, according to its type, and so on. And the last one, local strategy, is vocalizing. Now, this is also very, very important. As you can see from the word vocal cords, we all know, vocalizing means saying aloud. Okay, but what is important is you don't vocalize a text you're reading as a habit. In our education system, people are trained to vocalize the text because the teachers ask one student to read a text, a sentence, then another, and then another, because of which people get into the habit of vocalizing, which is a faulty reading habit. Vocalizing is only done and should only be done when you are not understanding something. And therefore, it could only be used as a fix-up strategy. जो मैंने आपको रीडिंग के लिए भी कहा पहले, as a fix-up strategy, not as a way of reading. So you vocalize because you have not really understood. Sometimes you're distracted. Sometimes you're not able to pay attention, and you read a chunk of the text aloud so that you can understand it, so that you can pay more attention and get more focus. Okay. So vocalizing is a very, very important strategy, but it's a fix-up strategy. So shouldn't be used all the time. हमारे यहाँ ये जो लोगों को आदत पड़ी हुई है कि पूरा टेक्स्ट वो पढ़ रहे हैं जोर से, या अगर आवाज नहीं भी आ रही तो होठ हिल रहे हैं, वोकल कॉर्ड्स हिल रहे हैं, that brings down the reading speed. As I said earlier, J.F. Kennedy used to read at the speed of 1,500 words per minute, but he can speak at the speed of 133 words per minute. So if you're going to read aloud, if you're going to vocalize all the time, your reading speed is bound to come down because you cannot speak faster than 133 words per minute, which is comprehensible. Okay, now some global strategies. Good readers do planning. They plan how they're going to approach the text, what strategy they're going to use. So I've listed so many local strategies, and there's some global strategies here. They plan how will they approach the text, what is their purpose. If the purpose is knowing the main idea of the text, then they will look at the first sentence of each paragraph to understand what is the heart of this text, okay? And that's the strategy they're going to use, identifying the main idea or the thesis statement. But if I ask them to know everything in detail, know everything in detail, then the strategy they are going to use is going to be different from just knowing the overall gist of the text. But if I'm going to ask them to quickly give me a date written in the text for invention of something, then they're going to not read each and every sentence or word. They're just going to move their eyes on the text quickly and do what is called scanning, so that they can approach at so that they can look at the date which is written in the text. And there's a difference between skimming and scanning. I hope you do know that. Skimming basically is getting an overall idea and overall feel of the text, the gist, to understand what this text is all about. And we do skimming a lot when we open newspapers, for instance, because when you open newspaper, you don't look at all headings, all news in detail. You look at the headings and you try to then understand, get an idea of what this is all about, and then you select the headings which you want to zoom in to understand. And that's what you do, which is skimming. But sometimes you do scanning, which is looking for a specific word or date or name or whatever, okay? And scanning is a strategy that you use a lot while you are using a dictionary, for instance. Because in dictionary, you don't start reading the words from A to Z. You zoom straight into the word that you want to know the meaning of, and for that, you scan the dictionary. Directories are also used for scanning purposes, where you just go straight to the name to see the number. Well, we don't have really directories now, but when we used to have them, that's the skill that was most important and mostly required. Okay, so those are important, and therefore you plan what strategy you are going to use for what purpose. So if you're looking up a meaning of a difficult word, then the reading strategy you're going to use is going to be scanning, okay, and not reading, getting the main idea, for instance. Okay, the next strategy is making connections, as somebody has already mentioned, making associations, connections between what you have read before in the text, so what have you read in the previous paragraph, and what is coming up in the next paragraph. And not only within the text, what is it that you already know? Remember, it's building a bridge between what is known and what is unknown. So making that connection between known and unknown, and connection between what you're reading in the text. So you can imagine reading is quite a difficult task. It's not easy, and therefore people doze off while reading, because you have to be mentally extremely alert, and you should be willing to put in effort, as I've said earlier, to be able to understand and remember. Many people tell me that they forget what they have read. they have read it carefully, but they have forgotten. It's because they are neither making connections nor activating their prior knowledge, neither skimming nor scanning. If they don't cognitively get involved in all these processes, then they tend to forget, and then they tend not to make connections. Okay, the third global strategy is using background knowledge and personal experience. Good readers bring into use, as we have said earlier, prior knowledge and whatever they know from life to understand what they're reading. And you all understand that, obviously. Another is hypothesizing, which is obviously very common in your field. I don't need to explain that. You hypothesize all the time what you're reading and guessing that this is what it is all about. And then as you read, your assumptions, your guesses either get confirmed or disconfirmed. Visualization, somebody also mentioned that earlier, which means you visualize, you cognitively, mentally visualize what the text is all about. And this is very easy to do on sciences text as compared to, let's say, fiction. But it is done in all types of texts. Even if you are reading a newspaper article, you are encouraged to visualize because that helps you understand what you're reading, and that helps you remember what you have read. Commenting on strategy use, which means whatever strategy good readers use, they also comment on the use of the strategy, which means, in other words, they are metacognitively aware of what strategies out of the strategies, for instance, I've shared, they are using. And lastly, they react to text. They agree with text and they make judgments about text, whether this is a dated text, this is an appropriate text, this is not an appropriate text, you don't agree with the number given here or the figures given here or the dates given here or even the ideas given here, which in other words means good readers are critical readers. Critical readers give personal response to the text. They do not immediately agree to everything which is in the text. They question it, they challenge it, and sometimes they say this is not right. What's written here is not right and they check other books to make sure that what they think and whatever prior knowledge they have is confirmed or disconfirmed by the text. And I'm sure we all understand this very well. Okay, so these are basically the strategies that readers use. Some of these they use before reading, some of them they use while reading, and some of them they use after reading. What is very important in conclusion, I would say, is that good readers just do not read to get away with reading, to get over with reading. They read because they have a purpose in mind and they put in effort. Poor readers think that successful reading is the result of luck, whereas good readers know that good, effective reading is the result of effort they put in reading. So this is a misconception between good readers and poor readers. Poor readers say, well, I'm not very lucky, I don't have that kind of background, I'm not a good reader, and they're not even willing to put in effort in that. Good readers, on the other hand, are willing to put in effort, and they therefore result in, and that results in understanding it. Okay, so that brings us to 229. Thank you very much for your attention and for being here in the talk. If you have any questions, I'll be more than happy to answer. Thank you very much. And thanks, Sajid, for inviting me once again.
Thank you very much, Dr. Bushra, Aman, Khuram Sahaba, for your great presentation, reading effectively. I hope so many participants learn a lot and enjoy it too, because this is very interesting. So. It's very interesting subject as well. So I think Sajid Khan from UAF have the question.
Please go ahead.
From University of Faisalabad.
Okay.
Sajid from University of Faisalabad.
Can you read the question, Sajid? Because
no,
I
just
can't.
Only raise the hand. Okay.
Oh, okay. Okay, so maybe he can unmute himself. Can he?
Yes.
Okay.
Now you can ask questions, Sajid Khan sir, from our great professor. Professor Bushra.
Yeah, I'll be more than happy to take it.
Sajid, please open. Sajid Khan sir, please open your mic.
Please unmute yourself.
Okay. Ma'am, we have so many participants, but unfortunately, in different three, we have created three systems. So one have the 65, other one had more than 100 people are listening us.
Wonderful, wonderful.
Okay,
That's a great achievement.
Sajid sir, please.
If you have a question, or you could even, Sajid, type it out. If it is difficult for you to unmute yourself, you might want to type it out.
Ma'am, personally, I have so many questions, but I will come myself, University of Karachi.
You're more than welcome. You're more than welcome.
Thank you, thank you, ma'am.
Thank you very much, for Sajid, once again for inviting. It was really a pleasure to be here. Thank
Okay,
you.
we have one feedback in the chat. So
Okay.
it was really a very inspiring session, a nice presentation. Thank you, ma'am. It was a great session from and from Maheen Abbasi, a good session. Okay, thank you, ma'am. Thank you
Thank
so
you
much.
so much. Thank you very much. Thank you.
Your presentation is very nice. I am hearing 2 days.
Thank you. Thank you so much. And I'm so glad for you that you give your feedback, Sajid.
Okay. Now I would like to invite Professor Dr. Sardar Sikandar Hayat. Sir is an Associate Professor, Department of Physics, Faculty of Basic Science and Applied Sciences, International Islamic University, Islamabad, Pakistan. Sir, I welcome you in this session, and from the behalf of Department of Metallurgy and Materials Engineering, Dawood University of Engineering and Technology. Sir, over to you, Sardar Saab. Sir, over to you. Welcome, sir. Welcome here in. सर आपके माइक खोल दें सर, माइक खोल दें सर, सरदार साहब। टॉप राइट ऑफ स्क्रीन सर, राइट साइड पे आपका माइक है, उसको अनम्यूट कर दें। टॉप राइट पे ऑप्शन है आपका आ रहा है।
हाँ, कैन यू हियर मी राइट नाउ?
यस सर, यस सर। Yes, sir.
Can I share my screen?
Yes, sir. Sardar Saab, please share your screen, please.
Hello, can you hear me? Is it working right now?
We can hear you very well. Yes, sir. इसको स्क्रीन को बड़ा कर दिया सर, तो बड़ा अच्छा हो जाएगा। और
Yes, it is possible for me right now. I think I can. Can I start?
Okay, great, sir.
Bismillahirrahmanirrahim. Good afternoon to all participants and students and colleagues. Today's my topic is anharmonic effects at the surface of silver 11 in the presence of copper small atomic clusters. The presentation layout is first of all I want to introduce the some basic terminologies, and then I will give some motivations of this work, and then some explanations of the molecular dynamics, and then calculations of the technique, and then interatomic potential, some fundamentals of the thermodynamic ensembles, then some informations about the boundary conditions, and some molecular dynamics examples, and then some references. Motivations of the research. Surface epitaxial growth and surface phase transformation, heterogeneous catalysis, nanostructures, thin film deposition, crystal growth, cutting and welding, and surface reconstruction. Actually, the main idea about the thing is actually we are going to do some simulations, and you have some idea about the simulation. Simulation actually, which is the bridge between the theory and experiment. We can say that those theoretical problems which are a little bit difficult to perform experimentally, we can take some helps to understand to do the experiment before to do the experiment by doing some experimental modeling, to do some experiment on the computer. And on the other side, if some results are available from the experiments and some informations, some are hidden, we can explore the processes which are little bit difficult from the to observe experimentally. We can explore those informations, we can get those informations which are beyond the reach of experiments. So then we can say that this is the bridge between theory and experiments, and the main idea behind the story is that we are going to do some surface diffusions of the islands, clusters, we can say that, and particles. Those are adsorbed on the surfaces. These are not absorbed, these are adsorbed on the surfaces. Actually, when we do some epitextual layer growth, we can say that some atoms at the edges of the epitextual layer may get some anharmonicity, and they may dislocate from the layer, and they may get some disturbances, and they may diffuse on the surface. On the other side, when experimentally we cutting and welding, during the cutting and welding, some atoms may not essentially becomes the part of the crystal, and they may escape from the experiment, and when they reach again the surface, they may adsorb on the surface, and they may some disturbances on the surfaces. We are going to see those disturbances which can be carried out by the adsorption of the islands or clusters on the surfaces. They may change some physical properties, thermal properties of the materials. We can guess some they to do some defects on the surfaces, and in the presence of those clusters, we can see some type of defects on the surfaces, some type of anharmonic features. We are going to see those features right now. There are three types of the major simulations when we think about the computer simulation. No doubt there are a number of techniques, while we can consider only those ones which are related to our problem, such as Monte Carlo simulation, molecular dynamics, and the density functional theory. These are actually, we can calculate the physical properties, thermal, electronic, and optical and magnetic properties of the materials. And if we want to see some bulk and surface type properties on the large scale, we can say that the Monte Carlo and molecular dynamics are the preferable techniques rather than the density functional theory. On the other side, the density functional theory is the quantum mechanical approach to investigate the electronic, optical, structural, and magnetic properties of the materials. Now, the fundamentals of the molecular dynamics. We can say that the molecular dynamics is a computer simulation technique in which time evolution of a set of interacting atoms and molecules is followed by the integrating their equations of motion. These are the just flavor of the basics of the classical mechanics. This is not the whole story of the simulation. This is, for example, we have the n number of the particles, which we can say these are the number of the atoms, and we are considering over here the number of particles, and then we can calculate the force as a function of n number of particles with the function of the acceleration, and can be derived in terms of the gradient of the negative gradient of the potential, and we can find over here some accelerations, velocities, and the positions of the trajectories of the particles, and we can say that these are the particles are part of the solid actually. Then the momentum of the particles as a whole crystal will be equal to 0. This actually molecular dynamics, actually our problem is just like those physical properties which are dependent on the temperature and the time diffusion on the surfaces. That's why we followed over here or preferred the molecular dynamics rather than the other techniques. And on the other side, this is a very reliable approach which is very near to the experiments, just like this comparison showing over here. If we take the experiments on one side and the simulation molecular dynamics technique on the other side, we can see that over here that in experiments we prepare some samples and then connect sample to the measuring instruments, then measure property of interest for set of time intervals, and then we can take some averages of those quantities and to avoid the noise. And then we can, on the other side, molecular dynamics are also same type of approach. If we take some system of particles, we can solve the equations of the motions, then we can extract the positions and the velocities of that data and use those statistical mechanics to extract the other physical properties. first of all, when we are going to do the simulation, keep in mind always theoretically we take the positions of the atoms. These are the not just like the real things. We have to give some boundings among the atoms. Let's suppose we start from very beginning. As a Hamiltonian, we know that this is the sum of the kinetic and the potential energies. Here, kinetic energy is in the form of the momentum, and here it's not difficult to find the kinetic energies. While on the other side, the potential is potential energy. How to guess the potential energies? It's a difficult task. For that, when we have number of atoms, those actually be a part of those atomic oscillations, we can be changed with the external stress and which can be varied with the passage of time and other parameters. We can say that this potential we start, that was just like we can say that if we have this is actually missing in the whole screen, the potential is just a pair interaction between the two atoms. Those are the function of the positions for two atoms. Just for the start, for the sake of the potential energy, we can say this is the Pauli repulsion here, and some part of the potential is just attractive, which attracts the atoms from the infinity. On the other side, they cannot be, they have some repulsion by the electronic overlapping. These can be extended in the well-known Lennard-Jones potential, and Lennard-Jones potential actually also known as the 612 potential. And this potential actually have to carry the two terms. First right term is the repulsive Pauli exclusion, which is due to the electronic clouds which cannot overlap with each other. On the other side, the right term here, which is representing the attractive term, this is due to the van der Waals forces. And this here sigma and epsilon are the new parameters. Epsilon actually the potential's depth means here when atoms are being a part of the crystal, they have negative potentials. On the other side, when we want to escape those particles, then we have to give some energies on the other side. And here sigma actually representing those potential value, which is when those value of R where potential is zero. So sigma and epsilon actually providing the informations of the minimum energy configuration, minimum potential, and the potential's value when zero. Those are the combining here the whole LJ equation. And this actually description of the closed shell system is very nice by using these one, just like noble metals like argon, krypton, and the while on the other side, for those systems which have very large number of atoms, it is not too good. We have to go for the other type of the potential. This is the actually graphical representation of the LJ potential. This is sigma here, where phi is 0, and epsilon actually the total depth of the well, where actually there is minimum energy where atoms should reside. No, at high levels, when the many number of the atoms, and we have to deal with those type of the elements which have just like electronic clouds in case of the metals, and in case of the we can say that there are in the case of metal there is a metallic bondings, and the forces are available between the nuclei and between the cloud of the electrons. Then we have to consider the well-established type of the bondings among the atoms. And the embedded atom method is a well-known method which is given by the Diane Vasquez in 1984, and they from that time right now it is used by over 15,000 theoretical calculations to do the calculations. This potential here representing the U of R, actually it carries two terms. Right one is actually the simply pair interaction, just like the Lennard-Jones potential, while the right one actually representing here the force needed to force due to the all electron density provided by the remainder of the atoms. While the left one, which is the pair interaction, this is electrostatic interaction. It is represented by the pair interaction. These phi ig of r is we can calculate by the atomic charges of the and the distance between the charges, and the electronic density can be, which is the function of the position, and the here z I is the it can be calculated by using these equations. These parameters alpha, beta, alpha, and nu are actually given by the this reference over here. These are actually carried some values for all periodic elements, and we can use those elements values for the calculations of the embedded atom method potential to the sake of interactions among the atoms to complete the story. This is a representation of the EM potential in graphical form between the force and the electronic density. This part is actually Water-Chen parameterization, and actually electrons clouds providing the background in case of the metals, and that's why this is the graphical representation of the EM potential. Now let's we have the atomic positions of the atoms, and we consider some potentials. In our case, we are going to do with the embedded atom method potentials, which is advanced one when we are doing some molecular dynamics. The question arises over here, the interactions up to limit. Actually, as I told that in previous slide, the atoms are interacting with each other, and the atoms are also interacting with the electronic crowd, which is provided by the conduction electrons in the case of the metals or conductors. Then it means all electrons are acting with those with the reference point. Here, let's suppose this red colored spherical ball is representing the atom. These are two-dimensional representation, and if we consider it is interacting with the first neighbors, then it will interact with 4 atoms in two-dimensional. Well, if we consider second nearest neighbors, then it will interact with 8 atoms. And on the large scale, we can say that up to 9 and 10 neighbors, it will interact with these number of 60 number of atoms. This is two-dimensional, and we consider in 3 dimensions how many numbers. There are a large number of atoms, so we have to interrupt the potential. Means we cannot afford over here to interact a single atom with the whole crystal atoms. If we consider this type of thinking, it will be difficult for us to do the calculations on the computers. There are large computational time is required to do the calculation. However, we have to think about what will be the cut of the potentials, how number of atoms will interact with this one to further reliable results. As in the previous slide, I show that when there is some after minimum position, there is some values corresponding. We reach that there is small interactions that remains. Then we can give the potential cutoff value. We take in our calculations over 9th neighbor distance, so that to save some computational time. On the other side, if we take the interaction with all crystal atoms, that will make some difficult story for us. Now the steps involving molecular dynamics, as I early make some story. First of all, we have to give some crystal preparation, giving some coordinates of atoms. In our case, we are going to take some metals. Those are the d block elements, and those are actually all maximum have FCC lattice with the coordinates, and at 0 Kelvin we give some coordinates, and then we will give some velocity initializations by a Boltzmann distribution, which is given over here, and then integrate the classical equations of motions by Nordsig algorithm. This is the computer program algorithm which have a time step of 10⁻⁻15 second in femtoseconds, and carry all the types of the equations over there to to calculate the Hamiltonians, energies, potentials, and forces among the potentials among the atoms. Then keep in mind we are going to do with on the computer, and we cannot take the infinite crystal, so that we have to introduce some periodic boundary conditions. We are going to take some supercell, maybe of 2400 atoms, maybe 2000 atoms. But in real, you people know that if we consider a tip, a point, millions of atoms are over there.
Slides,
so we have to produce.
Sorry to interrupt you, sir.
Yes.
स्लाइड तो चल रही है, पर किसी के पास कोई मसला है, इट्स ओके सर, कैरी ऑन ओके जी सर, डॉक्टर साहब कैरी ऑन.
To make the things just like real things, we have to give some periodic boundary conditions, and then I will explain the periodic boundary condition in next slides. Then we have to minimize the energy of the configurations, and just like the optimization of the system, then equilibrate the system. Then further we can start the other calculations. This is the periodic boundary condition. How this is, let's suppose we have taken this type of supercell, and this is not in reality we have to give some infinite positions of atoms. What we have to do? We have to give some periodic boundary conditions in 3 dimensions, just like by producing some image in such a way that the left one atoms are interacting with the right one, and the upper one interact with the lower one, and so on. In 3 dimensions, if we have some defect, it will reproduce in such a way. We can see over here that the yellow color ball and the red color balls are repeating. On the other side, if we have some defect, it means the defect is going to repeat. While we have achieved that the boundary effects are going to reduce, surface effects are going to reduce, because we have taken the images repeating in 3 dimensions. This is just like unphysical, but in computer we can do. Hello.
जी सर, आवाज आ रही है आपकी?
No, this is the story how it means this yellow ball atom is not interacting with this is the lattice constant, but it is interacting actually with the other unit, which is the image of this one. We can say that this is the length of the atom. The supercell is just like the lower line, which is horizontally representing that. To make the infinite system, the number of atoms that we have to consider during the simulation is determined by the number of atoms of the simulation cell. The distance between the atom I and j is defined as the distance between atom I and the closest image of the atom j, which I previously described. Now, this is the we take the potential cutoff, which is the R cut actually. Now, at the minimum level, we have to make the story in such a way that it will complete this spherical ball in just a way by reproducing the image in 3 dimensions, and these will be completed by the periodic boundary conditions. The atoms are interacting with their own images, totally unphysical, as I said. While in computational, this is we have to do only if L greater than 2RC, we automatically satisfy the conditions, minimum image conditions. Every particle I interacts at most with the closest image of the particle j, and these are the actually things we can see. Though let's say we have a supercell. For the purpose of to creating surface, we have to give the periodic boundary conditions in 2 dimensions, which is the surface required. In that direction, we have to give some fixed boundaries, so that image not is developed in that direction. Now, during the simulation, actually this is the molecular dynamics, and we are going to focus on the dynamics of or oscillations of the atoms. We have to take the time step of the in such a way to all calculations to do the huge programming which is behind the story. In case of equipartition theory, between working behind the story and the conjugate gradient approximations are working behind the story, we have to take the time step in such a way that our atomic oscillations can be recorded. If the characteristic period of the time tau is in such a way that delta t less than tau actually representing here the atomic oscillations, and we have idea about the atomic oscillations in the form of, we can say that the period of the atomic oscillation are in 10 to minus 12 to 10 to minus 10 to minus 12 to minus 10 to minus 13 second. We have to take the time step less than this one. That's why we taken over here in Nortzig algorithm in femtoseconds to catch those events, to catch those oscillations which are occurring over there in the molecular dynamics. There are three types of the ensembles which are going to use over here. First is the NV ensemble, which is microcanonical with conjugate gradient method to minimize the structure or optimize the structure for the relaxation, and NVT canonical ensemble, which is to use to thermalize or equilibrate the system, to shake the systems. On the other side, NPT isobaric isothermal ensemble, which will be used to attain the temperature for the simulations, and while to see the long run or to see the dynamics which will be evaluated with the passage of time can be seen with the NV ensemble. Now, first of all, energy minimization by conjugate gradient method. There are left side actually representing the two photos, one with the steepest descent approach and other one is the conjugate gradient method, lower one. This is the optimization way to relax the structures. On the surfaces, actually atoms just relax towards the inside the bulk, and the way how crystal as a whole relaxed can be seen here. And the right one, it takes some attempts again and again in number of 600 plus iterations. The energy of the crystal becomes ideally constant, and we minimize the structure by the conjugate gradient method. Energy of the crystal here along the y-axis, and at 700 Kelvin actually this is the process. And for copper 11, we increasing the number of iterations after a perpendicular cut, the value of energy becomes constant. The surfaces relaxed, here we have seen that the relaxed and unrelaxed surfaces for copper 11, copper 31, copper 210, these are the values for the relaxed and unrelaxed. We have seen that there are a little bit difference on the surfaces, while in bulk there is no relatively or we can say that there is no noticeable differences inside the bulk. This is only appreciable at the surfaces. NVT simulation, this is the pattern for the 10 picoseconds at 900 Kelvin, temperature versus time. We can see that this is the how it makes the system to equilibrate and how it is going to reduce the noise. It requires actually 20 picosecond. It is I given over here just for 10 picosecond. That's why it's a little bit remains some noise to confirm the system thermalized. We have to give some 20 picoseconds. This is the NPT ensemble to raise the temperature, and this is how we came from 600 to 300 Kelvin. And this is the first of from left to right. This is there is some major fluctuation, then it's going to decrease, and so on. However, small fluctuations will remain over there. This is actually how we can do the isothermal isobaric simulations at a specific temperature. We can say that on the other side, to attain temperature to do the simulations. Now, simple statistical quantities which we can measure during the molecular dynamics, which we have to face. Let's suppose we have a generic physical property A, which is the function of velocity and the positions at any time t. We have to take some averages of that physical quantity, and we can, if we have position coordinates and then we can calculate the average potential energy, which is the function of position. We can calculate the average kinetic energy, and we can calculate the total energy. We can find the temperature by equipartition formula. We can calculate the mean square displacements and the diffusion coefficients. This is the MD4 diagram. We have to give some initial coordinates, then we assign velocities, then we have to do some Newtonian equations, we have to solve some equations, then after that we have to minimize the structure to equilibrate the structure. We can say that the optimized structure, and if there is some equilibration, there is some problem, we have to again and again make some iterations, and then we have to do some products dynamics. We can record some statistics. We can further to do raw data to do the other required physical quantities and so on. Some examples of the applications. This is the lattice parameter of the silver. Comparison between the simulated and experimental values. Lattice parameter we have seen over there for the silver, which is very closer to the experimental ones, and we compared with the Clinters et al. Also, we have seen that that guy actually given the values with using the tight binding potential, and the difference between the calculated and experimental values was very small. Those were in the 0.75%. We can say that 0.0031 nanometer are higher, while on the other side the trends are same. Why these values of experiment are a little bit low as compared to the calculated values? The reason behind the story is that the calculated values which we done over here, actually these are the ideal crystals. On the other side, experimentally there are some defects are available, and that's why a little bit lattice parameter changes. However, the trends are same. We can say that this is very near to the experimental ones. These are the snapshots of the copper pentamer diffusion. Keep in mind these spherical balls are representing the atoms, and blue color atoms are actually representing the silver atoms, and the red color atoms are actually the copper atoms. These are absorbed on the surfaces. These are not the part of the crystal. And we increase the temperature, and we saw with the increase of the temperature, we saw these red colored atoms changing their positions during the simulation. We saw some photographs which are representing over here. There are nice photos of the copper atoms, and this is the same. We can think just like we old-fashioned ladies. They always separating the chaff with from the wheat. They just vibrating the substrate while the things are going to separate. These are just like our threshers of wheat. They are separating after there is not pulling in specific direction. This is the vibration of the substrate, and the upper atoms getting some dynamics from the lower atoms, and they are going to change position because these are not the part of the crystal. Actually, they are all absorbed on the surface, while on the other side the atoms of the crystal, they are bounded. They cannot leave from the surface, while these atoms can change their positions, and that's why we can say that they are diffused, two-dimensionally diffused. This is the surface diffusion, and we have seen the last peak. There is a pop-up of an atom. One atom becomes popped up over the other four atoms. This is the pentamer island on the surface, and we saw here very nice and beautiful pictures of the during the surface diffusion. This is the center of mass of the pentamer on silver vermilion. Variation of this island, which is the pentamer, with the time we have seen that in the left one is at 500 Kelvin, while on the other side this is at 700 Kelvin. We saw over here that the variation in the center mass at high temperatures is relatively more as compared to the lower one, and this is the function of actually time. And we can also see with the change in positions, just like a movie. I will show you in the next slide maybe. This is the RNS plot. We calculated actually the center of mass, MSD, then the diffusion coefficients. RNS plot actually here of the diffusion coefficient of copper pentamer. This is the diffusion coefficient formula here, and the RNS plot actually providing some. So we can calculate the excitation energy barriers from the slope of that one, and the inset displays the mean square displacements for the pentamer cluster on silver 11 as a function of time at 300, 500, and the 700 kelvins. These are the trajectories of the center of mass. This is the 7 copper atoms on the copper 11 surface, and the 7 silver atoms on the silver 11, and the next one the copper on the silver one. We can see that with the increase of the temperature, this is actually the trajectory of the island at 400, 550, and the 700 Kelvin. You can see that with the increase of the temperature, the trajectory shows that the major part as a black because it moves enough. And we can make some comparison in case of the copper and the silver clusters. We can say that the silver's dynamics are slightly less as compared to the copper, while with the increase of the temperature, both are going, trends are the same. The diffusion rate is going to increase with the increase of the temperature. This one is actually the copper on silver. Those cases were actually homogeneous, while this is the heterogeneous case. Their copper on the silver 11 surface, and the copper actually here also showing the same attitude with the increase of the temperature. We saw over here that the trajectory followed by the center of mass is going to increase with the increase of temperature. It means that the diffusion rate is going to increase with the increase of temperature. While it means there are a number of types of the processes right now involved in the diffusion process. Now we can give some reason why these are the different behavior. Both three cases, two for the homogeneous and one for the heterogeneous, are showing some different attitudes. Actually, copper and silver. In case of the copper, the copper radius atom size is almost 30% less than the silver. These are the energetic. These are the that's why copper's diffusion is relatively high as compared to the silver one. While on the other side, when we take the heterogeneous case, copper silver, then the copper silver have the bond length variation almost into 27 to 30% variation, and that's why the all competition between the atoms to get minimum energy configurations a little bit high, and that's why the diffusion rate is going to increase. This is the diffusion coefficient for the all. Actually, I represented over here only one island's story. While for all islands, we saw over here that from 1 to n atoms, with the increase of the island size, we have seen that the diffusion rate is going to decrease. These diffusion coefficients are actually at 300 Kelvin, 500 Kelvin, and the 700 Kelvin. So then we can say that with the increase of the island size, the diffusion is a little bit difficult because now the mass is going to increase, and the more energy is required, which is actually provided by the dynamics of the lower layer substrate atoms. This is Arrhenius plot, and this is providing the energy barriers and the attempting frequencies, how they are going to take some steps which are frequently involved in the surface diffusion. This is the effective energy barrier. Effective energy barrier we have compared with experimental ones, and we saw over here that the effective energy barriers are very near to the experimentals and the other theoretical results which were taken by the Monte Carlo and the statistical theory. Our results are very good and in the range of the experiments. Processes, number of processes observed in the surface diffusion, hoping the change of the position of the atoms from one energy minima to another energy minima on the surfaces. We have some idea about the surfaces. You people have, if we consider the 1-1 surface of FCC, that carry some energy minimas, and atoms should sight on the minimum energies, not on the maximum energies. So there required some energy barriers to go to the next energy minima. To do this one, it has to face the hopping process and the pop-up knocking out of one atom from the surface of the crystal, normally in the upward direction, and anchoring. If one peripheral atom changes its position and regain its original position again and again, that is anchoring and the breathing. Atoms of an atom tends to move but not able to change its positions practically. This is actually that is trying to do, and the sharing, sliding of only one line of atoms along the other line of atoms on the surface of the crystal, that is sharing, and the concerted motion if the whole island of the atoms changes its position from one place to another place collectively, that is known as the concerted motion. These all steps are actually part of the surface diffusion. Sometimes they only one atom, single atom, two atoms, and then sometimes the many number of atoms are involved during the diffusion. No doubt, for the large islands, the only peripheral atoms are the part of the dynamics, while the inner ones are maybe on the other word we can say the static. But with the increase of the temperature, they all followed the dynamics. Diffusion parameters for the 1 to 9 atoms, copper on the silver 1. These are the parameters. These are the actually diffusion coefficients at 300, 500, at 700 kelvins. We have calculated the energy barriers. We saw over here that the energy barrier is going to increase with the increase of the island size, because there is required push energy high as compared to the lower one, which is very small in case of the monomer, which is very aggressively move on the surfaces. Diffusion prefactor, which is actually providing the attempting frequencies, and these are the parameters, and which provide the all story of the diffusions of the surfaces for the islands. Copper trimer behavior at the silver 1 surface. We saw over that in the presence of the copper, there are some fissures and dislocations. 10 true dislocations are appearing on the surfaces due to the weight of the island. And on the other story, we can say that here the copper silver bondings are overcome on the silver bondings, and that's why the silver atoms a little bit stretched towards the island, and we saw that there are some fissures very near to the, which are near to 2 angstrom to the island, and 2.5 angstrom dislocations are appearing. And the lower one picture actually representing some vacancy formation. There red colored are actually island atoms, while the blue colored atoms are the substrate atoms, which is silver over here. Here we saw that with the increase of the temperature at 700 Kelvin, the substrate atom popped up, means the surface atom becomes absorbed atom, becomes a part of the island. This is indigo color actually representing here, which was the part of the surface, and now it is popped up, and now it can move on the surface, and it is not the part of the crystal right now. But during the diffusion, we saw with some passage of time, one atom of the copper absorbed in the surface, which is representing by the last picture, which is with the green color here. This atom take the position of the surface and becomes the part of the surface, and now the absorbed cluster here, 3 atoms are not the same type of atoms, 2 copper and 1 is the silver, which can move on the surface. They can move, but we saw over here that the copper atom size was less than the silver. That's why there remains some lapse well over there. Already this is the lapse well, which is created by the vacancy formation, by being a atom pop up knocked from the surface. Then other one atom, which was the part of the island, now becomes the part of the surface, which is representing by the green color here. Remaining some lapse well over here, because the size of the copper is less than the size of the silver. Due to the lapse well, this island remains stick to that well, because there is some kink for the island. It's difficult for the island to move from that position. So at very high temperature, it moves from that one. No doubt it moves. However, it stick for a time, almost 40 to 50 picosecond on that position, where it makes some exchange of the substrate atoms with the island atom. We also saw that the migration of the vacancy here, left one actually representing the rectangles, actually representing the dislocations, while the circles are representing the fissures. We can saw here the migration of the vacancy, the yellow colored atom, which is right side of the in left picture, and the right one we can see this is on the top and the left side. Right picture, that yellow colored changes the position. This yellow colored atom actually makes some sense of migration of the vacancy. And the popped atom is now indigo color is lower one. We saw that with the passage of the time, this is actually in 0.5 picosecond. We saw that the dislocations, the dislocations are attracting each other. They come closer to each other, while on the other side, the fissures, they moved away. And on the other side, we can say that the defects are attracting each other. These dislocations are the normal defects of the crystals, while the fissures are the gaps which develop due to the atomic oscillations. They cannot attract each other. No way. They have to move away each other, while the dislocations are attracting each other. In next slide, this is the snapshot of the ternary, copper, zirconium, silver alloy. This is actually very interesting results. These are three atoms of the species, those combining the cluster, trimer, hexamer, and the nonamer. These are the pictures of the. Hexamer is missing right now. Trimer and nonamer and the decamer. These are the different snapshots, and we saw that there is a formation of the vacancy in second row and some migration of the vacancy in third picture, and some migrations of the atomic diffusions due to the island. On the other side, we saw without these islands, there is no this type of the defect. These defects are actually due to the weight of the island and the forces between the host and the guest atoms. And these actually host guest atoms, the bondings overcome on the bulk bondings, and that pull the atoms from the surfaces. And we saw that these make some inharmonicity. These create some disturbances on the surfaces. These change some fields on the surfaces. And we also saw some exchange of atoms. Blue colored atoms are actually right now in part of the island. This is the atomic exchange process here, which was seen in the previous one, how surface silver atom becomes part of the island, while on the other side, the island atom becomes part of the surface. Here, actually, zirconium atom is too energetic in this one, which is a lighter one, and it's so mobile, and it becomes part of the surface, and atomic exchange process is just represented here. These are blue colored atoms are actually the surface atoms, while I atom, which is the surface atom, how it gets the position of the surface, and the surface atom K, which is going to pop up. This is the whole story of the atomic exchange process. Center of mass for the ternary, copper, zirconium alloy cluster, and we saw that this is the whole story of the variation of the center of mass for the trimer, hexamer, nonamer, and the decamer. We saw that the trimer is moving very frequently, and a little bit this was seen in the hexamer case, while in the case of nonamer and decamer, the dark spots are representing that it stays for enough time island over there. And for the decamer, the very small diffusions are found over there, but with the increase of temperature, we saw some diffusions because the island size is right now increased, and there is enough energy required to move the atoms, to change the position of the atoms. This is the potential energy of the ternary, copper, zirconium, silver alloy cluster. We saw the variation in the potential energy of the island with the passage of the time. There are certain jumps; those show some anharmonic features. We saw that over some breakage of the island. This is actually sudden jumps actually representing the breakage of the island, some distortion and anharmonicity in the crystal. These are the conclusions. We can say that this is actually how the simulations are going, and we can show some movie of the whole story. There is two large computational resources behind the story, and I just basics are given over there, while the big calculations and the big potential bondings and some interactions and so many algorithms involved behind the story. This is the island atoms which are the diffusing on the surface, while these are the atomic oscillations. Keep in mind, these are the oscillations which are in angstrom. These are in angstrom, cannot be seen with the naked eye. If we take some dot on with a pen, then the millions of atoms can be over there. While here we are taking only 2400. These are 20 by 20, 400 atoms, blue colored atoms, while the 3-4 atoms are on the side. And these dynamics are at 700 Kelvin, which is a little bit. We have to focus 700 Kelvin. It's enough temperature, which is roughly cannot be achieved by simply way. We have to make some special configuration to do all these experimentally. We saw that with the increase of temperature, there are a number of things are going to increase. With the size of the island, diffusion is going to decrease. And hormonicity defects, blah blah blah. All these things were very long things, and these are actually helped us to avoid those problems which can be make some sense during some physical calculations. If there are some atoms absorbed on the surface, they may change their physical properties. You people have some idea during the workshops. Always they are going to make the clean things, because those atoms which may be absorbed on the surface can change the as a whole story. That's why these are the actually calculations which can give some idea about the experimentalists, how they can adjust the things, how they can control the things, how the parameters can affect the things.
Sardar साहब आपकी slides क्यों नहीं हो रही?
I finished the slides.
Okay, that's fine.
You have seen the movie? At the end, I saw some movie. I showed some movie. You saw the movie?
No, sir.
You were disconnected. I didn't disconnect. I think.
Yes, somehow, because I'll change the laptop now, so there is some problem with the laptop, and I have changed.
Sir,
ये first slide पे आ जाए, sir. Okay, thank you. I welcome you, sir, here in this symposium.
Thank you very much. Hi, dear distinguished scholars, engineers, faculty members, scientists, industrial experts, and all other worthy participants of NM's Talk 2020. Assalamu alaikum. I hope you and your families and loved ones are well and healthy. And first of all, I would like to thank Dr. Engineer Sajid Hussain Syal Sahab, Chairman and Faculty of the Metallurgy Engineering Department of Dawood University, Karachi, for extending all the excellent arrangement in the successful holding the symposium and giving me an opportunity to present here. With this best wishes, I will start my presentation. The topic: Advanced Nano System, Designing, Simulation, Characterization, and Prefabrication.
we are sorry for disturbance, Dr. Abdul Malik. Please, can you fully screen your PDF file?
Sorry?
If you will full screen your PDF file, just right click on the screen and full screen it, so it will be more visual to the audience.
Okay, wait please.
Just in the center of that PDF, right click and then press on the full screen. नो सर, आप उसके जो है ना होम पे जाएं, जो आपकी फाइल खुली हुई है आप दोबारा उसको खोलें और इसके बिल्कुल सेंटर में प्रेजेंटेशन आउटलाइन आ रहा है ना, यहाँ पे आप राइट क्लिक करें, अपने माउस से राइट क्लिक करें। नो सर, आपकी उसी फाइल पे आप जो है ना इसको राइट क्लिक करें और वहाँ पर फुल स्क्रीन आएगा। तो ओके सर, here you can see that there is
There is no full screen option here. Is it okay now? Screen option here.
Okay, sir. Open that screen. I again I will tell you here. You can see my screen. So please open that file. Share your screen.
Again.
Yes, again share that PDF file.
इनको तो रिमूव करें क्या ये शेयर तो करें अपन स्क्रीन
शेयर तो करें
हाँ
अच्छे भी डॉक्टर अब्दुल मालिक अच्छे yes can see
I have shared.
Okay sir, now open the PDF file please.
It's open.
Okay, so that's fine, you can continue sir, that's fine.
So I will start my presentation.
Yes sir.
My presentation is designing, simulation, characterization and fabrication of advanced nanosystems. My presentation outlines, I will introduce the nanosystems, nanosystem material, its designing, how it simulate, nanosystem materials, how it synthesize and growth, and nanosystem, how they will be characterized and analysis. And then I will go to the fabrication and development. Nanosystem definition, working with the matter down to the molecular level to create the structure and device 1 to 100 nanometer in size with fundamentally new organization, properties and performance. We can say a nanosystem is an instrument that responds to a physical stimulus such as heat, light, sound, pressure, magnetism or motion. That will take us to the realm where the properties of the material are dramatically different, demand new tools and new understanding, may hold the key to 21st century industrial revolution. Advanced nanosystem, I can say, if all the nanostructures elements operate at the same frequency, high degree of mutual coherence and emit, sense, detect or generate in phase with respect to each other, then we can say they are integrated, all the nanosystem. For example, nanolasers, nanogenerators, nanosensors and nanodetectors are examples of nanostructures. The array are extremely tolerant to a latest constant variation, allows composition to vary over a large range within a single substrate or structure. How nanoscale material categorization? Naturally, ultrafine particles are virus 10 to 60 nanometer, bacteria 30 to 10 micrometer, dust from desert 100 nanometer, and the ultrafine particles from established technology or byproduct by conventional process, combustion soot 10 to 80 nanometer, paint pigments 80 to 100 nanometer, welding fumes 10 to 50 nanometer, and diesel exhaust particles small modes 7 to 40 nanometers. Carbon black of photocopier toner 10 to 400 nanometer. Engineered nanoscale particles that are nanomaterials, fluorine, buckyballs 1 nanometer, nanotubes 1 to 5 nanometer, multiply of 10 micrometer, and quantum dot for medical diagnostic 5 to 20 nanometer. Semiconductor bars of sensors 10 to 100 nanometer diameter, multiply 1 to 1 micrometer. Why nanosystems are attractive? That is useful for information technology and quantum informatics, quantum electronics, just like logic memories, magnetic memories, spintronics devices, and for energy, large scale, low cost nanoparticle based on solar energy collection, high efficiency solid state lighting, and for health in situ drug delivery, diagnostic, action monitoring, performance enhancements. Environment, low cost nanosensor array for health safety, nanoparticle-based waste destruction, and manufacturing large area bottom-up assembly for low waste, energy-efficient manufacturing. How to build things at nanoscale? Conventional machines, 1 meter to 100 millimeter, just be built and assembled. And for microelectronics, 10 to 0.1 micrometer top down, just built in place. And for nanotechnology, 1 to 100 nanometer bottom up self-assembled. How to build things at nanoscale? Making nanomaterials. First of all, self-assembled, top-down, bottom-up, characterization of these nanostructures, imaging and measure the small things, understanding the properties. Nanoland lies between micro world and single atom and molecules. Nanosystem integration and performance. This is the high payoff area. How do we assemble the nanostructure into advanced nanosystem? Properties and application of nanosystems. Properties: mechanically strong and flexible, optically transparent, tunable optical band gap, monolayer, direct few layer, indirect band gaps, high thermal and electrical conductivity. Thickness depends optical and thermal properties. And the application of these nanosystems are high-speed electronics, transistors, ICs, and LEDs, transparent and flexible display, solar cell, broadband photodetectors, sensors, and memory devices. Practical application are at the early stage. The top 10 nanotech products of 2003 are high performance Skywax, breathable waterproof sky jackets, wrinkle resistant, stain repellent, deep penetrating skin cream, world's first OLED digital camera, nanotech's DVD and book collection, performance sunglasses, nanocrystalline sunscreen, and the 9 antenna high-tech tennis rackets and balls. Now I come with these motivation introduction to how they designed and simulate the nanosystems. First of all, the material for these nanosystems. As you know, the designing and simulation for a nano scale, we need a high speed of fast computing systems. So the construction of mathematical model, analysis of idealized models and hypotheses to describe the nature, physical phenomena by performing the idealized experiments on the clusters of computers. The triangular show, first of all, we have to do a computational design, then predict by experiments, and theory development, predicts, and again it's a cycle, test, predicts, test, and it's go on. The cluster system for these nanosystem for designing computers having Linux or Unix or ROX operating system, we have used laser mod here, Win2K, the density function theory codes, quantum espresso, ANSYS for microscale or MEMS devices, and also a console multiplex code for MEMS type devices, relativistic atomic program code and Monte Carlo, and some of Mathematica and MATLAB and MathCAD codes here. How the cluster, the clusters are working? They are working with a gigabit Ethernet networking modes. First computer master node and other are computing nodes. For example, numerical simulation for droplet surface temperature using console multiplex. We have developed the such theory. The boundary conditions consider the temperature fixed from droplet, substrate base temperature is fixed, and heat flow droplets. Numerical simulation of the droplet temperature using console. We have calculated such properties, construction, concentration, diffusive flux magnitudes, and the time scale with respect to the its spread. Comparison with these with the published data here, the console simulation, time versus temperature variation, surface temperature for substrate copper at 60 degrees centigrade. You can see here. and cross-section glass substrate for copper at room temperature. And the important factor now I want to share, the energy band gap. Energy band gap of a nanostructured material is one of the most important parameters for optoelectronics application. It determines the spectral features of absorption and emission process and other electronic and optical properties. Range of the band gap relies with high quality nanostructured material like chemical and thermodynamic limits. Traditional planar epitaxial method is heavily limited due to the requirement of latest matching. Larger the mismatch, nanoscale offers the unique opportunity for growing the nanostructured materials. Alloy structures are very dissimilar latest constants and band gap. And we use density function theory for that. And here is the model for how we can mathematical applications used for that. And with this theory, using LDO approximation, core electron replaced by the Tollin-Morton pseudo potential, and the calculation were carried out by such sizes are just for example, strontium titanate, bulk latest constant we simulate. And these are simulated by Cobb and the results show that as we increase the temperature, theta tends to decrease monotonically as the surface goes through a sequence of the reconstructions. With the help of V2K density function theory, using a density function theory code, we can find the absorbance. Maximum absorbance take place here from graph show a 1.6 electron volt to 2.6 electron volt. And we can find the energy loss for these such type of nanosystems. Loss of energy during the propagation of light and the material. Initially there is no loss. As the incident photon energy increase, there become maximum loss at 14 electron volt. Above the value of material behave as a metallic and below this electric. The other optical property, how many electrons are taking part in the optical transitions are calculated with the help of some rule by V2K. With the increase of energy, number of electrons are increasing. Maximum peak is obtained at 18 electron volt. It means 18 electrons are taking part in the optical transitions. And the other such function, dielectric functions, the real part and the imaginary part we can find, and with this we can simulate the optical properties of that material. Such like the reflections, as some value reflective index value is maximum, at some value falls below unity. The reason is the material absorbed at high energy photon at higher values. Maximum refractive index is obtained at first transition, and a higher value lower the refractive index show that the direct de-excitation is not possible, energy dissipate. And the reflectivity, maximum reflectivity obtained at 2.5 electron volt with some humps. These humps show that the inner band transition of the electron, and at maximum value of the reflectivity, semiconductor property material vanish and it behaves as a conductor at a high incident photons. And at the end, with the help of density function theory of V2K code, band structure calculation is a scale to investigate the material, whether conductor is insulator or semiconductor. With the help of this, valence band minima and connection band maxima lies at some symmetry points. They satisfy the direct band gap. And in optoelectronic devices, direct optical transition dominate over the indirect transition variation, 0 to 0.2 in our cases. The system was the CZT. And the density of states, we can also calculate total density of the state, gives the information about the collective behavior of all the materials. No peaks above 0, red and black lines showing the band gaps, higher peaks showing more number of density of state at a particular energy range. How the nanosystems are synthesized or growth. We are using here in our institutes also, there is a molecular beam epitaxy. When we did the calculation, density function theory calculation, then go to the system to grow such type of system, nanosystem. MB is an ultra high vacuum evaporation technique for deposition of extremely high purity crystalline thin film with the atomic precision. You can say the low log chamber etc. here, and it is used for growing the epitaxial layers on a single crystal wafer and for in situ surface analysis. We have graphene cells, gallium, indium, aluminium, silicon, magnesium, and beryllium etc. more. And this is equipped with the nitrogen RF plasma source, and also it is equipped with the in situ characterization tools, reflection, high electron refraction, read, and spectroscopic ellipsometry. With the help of that, we can real time characterize the growing nanostructures. For example, growth and crystallization gallium nitride and gallium arsenide based light emitting nanosystem. It's a LED or laser diode. First of all, we designed it with the help of laser mod. We can calculate the thickness of the layers and materials used for, and the optimized structure for LED or laser diode. For example, epitaxial growth of gallium nitride, aluminum oxide plasma assist MB and its characterization by rate, N-type doping, silicon of gallium nitride for gallium nitride, and P-type doping, magnesium for gallium nitride. Growth and characterization of indium gallium quantum well structure, and growth of the semi-insulating gallium nitride for radiation detectors, etc. And from figures you can see the optimized structure from laser mod, and then the read peaks in situ read images are showing that the crystalline structures are growing, and from the graphs you can see the growth of the single crystal growth of gallium nitride. Another very important system for the nanosystem growth, low pressure chemical vapor deposition, and at NILO, LPCVD. That is the chemical vapor deposition technology that uses the heat to initiate a reaction material. Its application, just like silicon dioxide thin film deposition and polysilicon thin film for silicon nitride, and deposition of film for silicon-based microelectronics, production of the microelectronics, mechanical system, NAM system, and optoelectronic material, and by CVD, LED, blue laser diode, solid state white lightning. Here you can see the schematic of these LPCVD system in the diagram, and above is the picture of that LPCVD system. And basic technique for thermal electron and beam evaporation, for with the help of thermal evaporation, we can also deposit the nanostructures or nanosystem. The deposition of different nanostructure material like metals, dielectric, semiconductors, nanostructure deposition of the semiconductor material, thin film for various optoelectronics application, and we can use such type of system for metal contacts. And the techniques are here equipped with a thermal evaporation, that is the inductive type of, and electron beam evaporation we can use. Reactive magnetic spectrum is the second one system. Pulse laser deposition system is also, we have the next picture is showing the pulse laser deposition system. That are used for anti-reflection coating, anti-reflection type of nanostructure material, high reflection coating, beam separators, growth of metal oxide by sputtering and thermal evaporator to study their response to the different gases and different types of material, such like aluminum nitride, silicon carbide, cuprous oxide, zinc oxide, and tin oxide. We can grow with the help of sputtering system, and good quality films we can get. Growth and optimization, high quality crystalline aluminum nitride thin film by using sputtering technique for the application of optoelectronics. Fabrication of cupric oxide thin film based on transistors for application in electronics. And the other system for the synthesis or growth of the nano system, that is the electrospinning and spray deposition system. Electrospinning is the fiber production method which used for electric force to draw the charged thread of polymer solution up to the fiber of 10 nanometers. The system is equipped with a syringe pump, nano mover, power position systems, and power supply 50 kV, 0 to 30 milliampere currents, and Dell Electronics Corporation, that is, and the collector is circular copper plate rotating aluminum drum mesh interdigitating electrodes. We can spray coating, you know, it is a basic technique, is the coating technique where a device spray a coating, paint, ink, varnish through the air into the surface. Air bushes spray gun we use here. And the next other system is chemical vapor deposition system. With the help of this, showing nanostructures here in the diagram, optical image of CVD grown indium selenide at the different growth time of the flow rates with different flow rates. Here the flow rate growth time of the growth speed of both edges would be identical, vanadium, selenium, and indium, which result in the hexagonal shape. At lower organ flow rate, the growth time, the growth rate of selenium edge, vanadium and selenium, and in the edge vanadium, indium is either vanadium or silicon, and vanadium or selenium is greater than vanadium, indium. Shape of the flag transferred from circular to hexagonal with increasing the flow rate and growth time. Flag shape depends upon the edge minimum energy of the element in the symmetric crystal of construction model C. Above the schematic of the CVD system, it is just a cord with the which is equipped with the quartz tube and with the optimized flow rates of different gases. How the nanosystems are analyzed or characterized? The system use X-ray diffraction technique. Here at the low, an instrument capability it is used to identify, determine the crystal structures, its parameters, size of the crystallite or grain size, texture, stress and strain, mole fraction, composition of light, phase and thickness of the layer of the film. We can use the X-ray technique. Some of CGT X-ray diffraction peaks as deposited. The above graph show multi-peak after annealing and intensity increases little bit, shift towards the left, show the small concentration of zinc, and CGT1 peak is between CGTE and zinc right, 25.77. CGT X-ray diffraction, again 4 peaks in the deposit samples and multi-peaks after annealing, little bit right shift indicate that excess form of zinc, and sharpness of peak testify their homogeneity. And the next tool after the X-ray diffraction, we can use the field emission scanning electron microscope for morphology. Field emission scanning electron microscope is one of the most powerful and useful tools available today for nanostructures and nano system. SCM use electron rather light to examine the surfaces, permitting much greater magnification, resolving the power and depth of the peaks. Field emission scanning electron microscope capability provide us the high resolution imaging at magnification up to 10 raised to power 6 multiplier. This allows us to examine the characterize the nanomaterial fractures, surfaces morphologies, composites, and their constituents and microstructures of the prepared cross section. Through the addition of energy dispersive EDX X-ray spectrometer, we can detect all of the elements above the beryllium atomic number 4 on the periodic table, allowing us to characterize the most material. And the schematic diagram of the field emission scanning electron microscope here. It is designed to perform an imaging with the low energy electron and ultra high resolution at the same time. The model is showing here an instrument capability 1 nanometer up to resolution and magnification 1 million, secondary electron imaging, topographic contrast, back scanning electron imaging, phase contrast, energy dispersive X-ray spectroscopy, and the compositional analysis we can done with the help of XRD EDX. Some pictures and some morphologies obtained by field emission scanning microscopy. For example, ZN nanowires, and clearly showing the structure. And these are the polymer fibers, TiO2 nanotubes, Ag nanoparticle on silicon deposited, structures grow, and the image of Ag particle on the antimicrobial dressing, and 10 nanospheres here, and TiO2 microspheres. And for example, EDX of the zero nanothin film, we can see the clear zinc and oxides are contents there with the help of EDX spectrum. The next important technique for analysis and characterization of the nanostructure, that are Raman spectroscopy, photoluminescence excitation, and the photoluminescence system for electronic properties characterizations. These systems are capable of excitation sources there, helium and cadmium lasers, 325 nanometer and 442 nanometer, DPSL 532 nanometer. And detectors are CCD, indium gallium arsenide. Resolution is 5 centimeter to 1 for Raman and 0.019 nanometer for PL. Temperature range 10 Kelvin at 2 room temperature. We can find the spectra with the help of such type of Raman systems. With the help of Raman system, material, we can identify the materials, structures, crystallinity, phase transition, polymorphism, and with the help of photoluminescence system, energy, we can find out the energy, band gaps, identification of impurity levels and defects, and material quality also we can find with the help of photoluminescence. Let's suppose a CZT Raman spectroscopy here. The sharpness and broad peak indicate how well and in much quantity that material exists. Redshift after annealing indicate that the increase of zinc concentration. Above figure, compare the above graph with the bottom below graph, we can see clearly the increase of zinc concentration. With the help of photoluminescence, single substrate, by controlling the spatial variation of the various elements and the temperature of a substrate, called the dual gradient method, we observe wide spectrum of visible light from different parts of substrate by optical pumping. The image clearly shows the different colors with the help of just the concentration of CGTE and zinc chloride NTE, we can change the color of CGT growth nanostructures. And over a wide range, we can use this type of material for emission detection and also for other purposes. The other important technique for electrical properties measurement, we can find the IV and CV and Hall measurement systems. This system equipped with the that is 4 SMU and 4 periampere amplifiers, input impedance 10⁻16 ohm, accurate greater than 10⁻16 ohm, accurate low current, pico ampere, and no leakage current due to the mechanical switching software used IV, CV, and Hall measurements. Resistivity we can find from such type of system for probe method. Resistivity we can find conductivity, mobility, doping concentration with the help of such type of Hall measurement system. And another important technique which can be used for morphology for nanostructures. Morphology of nanostructure can be in 3 scanning modes of atomic force microscope. One is the contact mode, non-contact mode, and tapping modes. The application in organic materials and organic materials, surface morphology, we can find out the roughness, surface potential, film thickness. For example, here is the tin oxide prepared by electron beam film, the topography or of the such nanostructures, and here is the silicon grating of the by another is the spectroscopic electrometer. An instrument capabilities: light source, xenon lamp, detector photodiode array, spectral range 280 to 100 nanometer, 1000 nanometer. We can find with the help of this thickness of the thin films, multi-layers thickness, dielectric constant refractive indexes, and extension coefficients with the help of spectroscopic ellipsometers. And then here also we use a model for the spectroscopic characterization. The films you have prepared. First of all, you have make a model, ellipsometric, or then fit the model to find out the refractive indexes etc. The variation of refractive indexes show with the wavelength nanometers here in the graph. With the help of spectrophotometer, we can find the optical properties like transmission, reflection, absorption, spectral range 280 to 2500 nanometers, and lamp are deuteron and tungsten lamp. Here is the principal diagram is showing the spectroscopy or spectrophotometry. Here is a U4100 Hitachi system using for the nanostructure optical characterizations. How we fabricate such nanostructure system for wide range of detection, emission, and shielding application. So, first of all, we have to simulate, then we synthesize and characterize, and then we must do the patterning or for packaging. So we need a photolithography system. Photolithography sequence of activities needed for the transfer of pre-designed pattern to. It is in the clean room, FS clean room of class 10,000. A number of particles 352,000.5 micron. Laminar flow Stardust unit class 100 and clean room air shower, eco air shower case to C1 air in our labs. The help of photolithography is also. This clean room is equipped with a spin coating and backplate system. Model 200 CB Brewer sciences. Maximum spin speed is 6,000 RPM. Maximum substrate size is 200 millimeter and maximum temperature is 300 centigrade. Mask liner UV exposure system is also showing in the diagram and also in the clean room of 10,000 and model ABM 6350 NU DCZD USA. UV lamps line 400 nanometer H line. Maximum substrate size is 100 millimeter 4 inch. Reactive ion etching system is also there. The model is showing here. Cry 200 AST and gases are chlorine, sulfur fluorine, bichlorides, and carbon fluoride, hydrogen, argon, oxygen, nitrogen, etc. RF power source also the Tesla 136 600 watt and 13.56 megahertz Caesar, and the substrate size is 4-inch wafers. With the help of such type of system, the MEMS devices can be designed. A let's example is the micro cantilever. A micro cantilever is a device that can be act as a physical, chemical, or biological sensor by detecting changes in the cantilever bending or the vibrational frequency. Vibrational frequency change, piezoresistive optical, and capacitive deflection detection method are used for the sensing application, and the steps are showing for the micro cantilever fabrication, patterning of such type of system. The application of micro cantilevers or chemical sensor. It can be used for pressure sensors also. CGT, as we did the calculation for CGT, so they emit how to emit a wide range application, allowing of 2 or more semiconductors to produce the quaternary semiconductor nanosystem, for example CGT, which produce continuously varying compositions of the element on a single substrate. By controlling the spatial variation of the various elements and the temperature of the substrate, called the dual gradient method, we can observe the wide spectrum of visible light from the different parts of the substrate by optical pumping. Band lineup across the 3 segments of heterostructure nanosheets, reflective index of the profiles at 455 nanometer, 430 nanometer, and 590 nanometer wavelength, respectively. The band lineup and reflective indexes profile of 3 segments and nanosheets are shown here. We observed a wide spectrum through the photoluminescence system. Also, this experiment did FMFAN published in Nature 2015, and the different color we have also observed in our laboratories, and the blue emission, also green, and also we have observed a white light emission. In the spectrum, PL spectrum, you can see the wide spectrum of the color emission. And with this CGT, we can also use to develop a nanosystem detector for using the other electronics like charge sensitive preamplifier, shaping amplifier, and so on, to use the nanostructure as optical detectors. What range you are using, we can change the concentration of cadmium telluride or zinc telluride in the nanosystem. Then we can use it for various applications such like microwave, infrared, and visible light application. We have also developed nanostructure used for gas sensing application, carbon monoxide, methane, also 400 centigrade temperature and 90 temperature. The nanostructures operate well. The results showing here: carbon dioxide sensing using ZNO thin film at 150 centigrade, when gas is on, then in the down peak, and when gas is off, then uptowns are showing in the graph. Also, such type of response from the nanostructure we have observed. Another important application of nanostructures and nanosystems that we have developed for shielding purpose, GOPB-GF, that is graphene oxide, and Persian blue graphene ferrites. We have used the composite of both by using the hammer method that are the graph represented here. XRD, the peak of GO are well matched with the previous literature. XRD pattern of the entire of this, the peaks are detected are shown for Persian blue, and graphites are shown in the diagram. With the help of Raman spectroscopy used to calculate the chemical analysis, and peaks of D and G bands were observed at 1309 and 1465 at the per centimeter, that is the wave shape. Hybridization sp2 and sp3 are calculated through this Raman spectroscopy. Reduction of graphene oxide and formation of ferrites and Persian blue confirmed through the Raman spectroscopy. Estimated hybridization cluster size sp2 formation in sp3 7.65 nanometer calculated through that relation. Photoluminescence spectroscopy of such system, the observed at 378 nanometer due to the reduction in the graphene oxide. By using the conjugate length and cluster size, the value of the disorderliness in the hybridization sp2 can be calculated. With the help of UV visible spectroscopy, the extreme observed at 217 and 325 nanometer in graphene oxide, and by reduction in Persian blue graphene ferrites shifted, the extreme is observed at 207, 258 and 693 nanometers. Peaks of Persian blue graphene ferrites are attributed to the pi-pi bonds and to the pi bond transition, ferric to carbon and then ferrite charge transitions. Imaginary imaginary part of the dielectric constant, dielectric loss tangent was increased with the rise in frequency, and at the certain critical frequency, dielectric loss reached its maximum peak value and then decreased at higher frequencies. The peaks observed in the dielectric loss curves are appeared, then the frequency of the electron hopping between ferrites 2, TD2, ferrite 2 and Persian blue is equal to the frequency of the applied field. The dispersion observed in the dielectric loss is due to the Maxwell interfacial type polarization and Pope's phenomenological theory. We can also find the AC conductivity as in an increasing behavior observed in the sample against the frequency variation, increasing thickness show and increasing behavior of the alternating conductivity, and AC conductivity calculated through the such relations. We can design a nanosystem for shading purpose. Our samples used for calculations, and we use for a shielding of the X band or any band of the material by changing its constituents. Sensing nanomagnets using nano vacancies, nitrogen vacancy centers in the nano diamond, single domain particles, all the unpaired electronic spins are aligned, and the dipole moments can flip along the line of easy directions of magnetization. The time between the flipping depends on the size and anisotropy. Magnetic properties or temperature are dependent. Iron oxide nanomagnets bond with the nanodiamonds. Optical nanothermometry using the nitrogen vacancy centers in the diamonds. We can use such system here. The conclusion of and comments and challenges, that is to design a nanosystem, the surface energy of the nanostructure to explain the set of a structure phase transition on the different surface structures. Density function theory simulation can be helpful to design the nanosystem. Nanostructure can be achieved over the complete composition range along the length of the substrate, resulting the continuous band gap changes on a single substrate with the corresponding light emission over the entire visible spectrum. All composition control can be achieved over the nanowires and nanosheets. One of the most interesting applications of such semiconductor alloy nanostructures with the wide range of available composition is a multicolor or full color emission, wide tunable lasing from a single substrate from a single nanosystems. New phenomena associated with small size, preponderance, again, that is the number of layers of surfaces, number of surfaces or number of layers and interfaces between the surfaces lead to a new modes of electronic transport, radical changes in the collective phenomena, new chemical reactivity, new mechanical properties. Here, the single molecule sensing showing in the picture, and also the strengthening of the nickel. Nanostructure material by design, manufacturing at a nanoscale, chemical, biological, radiological, explosive detection, nanoscale instrumentation and metallurgy, nanoelectronics, photonics and magnets, healthcare, therapeutic and diagnostics, efficiency, energy conversion and storage, microcrop robotics, nanoscale process of the environmental improvement, that we can use the nanosystem for above applications, and encourage conduct research on new manufacturing technology for material devices and system, develop the mechanism to transfer such manufacturing technologies to industries. Nanoparticle potential health risks, also the drawbacks. The properties change with size. Can some size composition, plus the compositions have adverse health effects, implications for environment regulatory system, same chemical, different forms, for example, carbon black, diamond, buckyball, nanotube, same chemical, different size, like titanium oxide, quantum dots, cadmium sulfide, cadmium cyanide, can nanoscale particles cross biological barriers, and what are our responsibilities and precautions in the lab, in the factory, in the environment, and in the consumer products. Ubiquitous nanosensors, privacy of the individuals. What if walls have eyes and ears? What if sensors can attach to me without my knowledge? Is my health and genetic susceptibility private information? Are human assistive devices for the disabled appropriate nanotechnology to support? Should nanotechnology be used to enhance the human performance for warfighters, for athletes, and for children? How decides which can? Thank you very much.
Sir, thank you very much. Abdul Malik Saab, thank you very much, sir, for your time and very impressive presentation. I would like to invite the attendee, if they have the question, they can ask, please. Is there any question from the participant side? Hello, मेरी आवाज आ रही सबको? किसी के पास अगर कोई सवाल हो तो आप काइंडली हम बताएंगे. Anyway, sir, thank you very much, sir. Abdul Malik Saab. Hello.
Sir.
Thank you very much, sir, for your time. Even we are glad to see you as a part you played for the Dawood University of Engineering and Technology. And inshallah, we will see you in physically in Karachi. We will arrange a physical conference. So we are lucky. We have a great friend like you, Abdul Malik Saab, a principal scientist from Pyaz. Thank you very much, sir. Thank you very much. God bless you. Now I would like to invite Dr. Adnan. Sir is an assistant professor in Department of Physics, GC University, Faisalabad. Adnan Saab is a very great personality from the GC University. So over to you, Adnan Saab. Please. Dr. Adnan Saab.
हेलो
जी, अदनान साहब एक मिनट, सर अब्दुल मालिक साहब कुछ कहना चाहेंगे, एक मिनट सर अब्दुल मालिक साहब.
I am glad to share with that distinguished scholars, faculty members and scientists, engineers and research experts and others joined the symposium from all over the world, participated actively and highly appreciated the event. I hope and pray for this sort of literary activities will continue on the regular basis. Thank you very much, sir.
And thank you for your support, sir. Thank you very much. Okay. Okay, sir. Adnan Saab, over to you. Welcome, Adnan Saab.
Sir, thank you, sir. So you can hear me clearly?
Yes, before to hear, we want to see you, sir.
Let me turn on the camera. Okay.
Okay.
So, yeah. I was actually just trying to share my screen actually. It's I think so. You can share my screen. See my screen?
Yeah, yes, sir.
It's rapid identification of bacteria using hybrid plasmonic platform slicers, right?
This आवाज थोड़ी डबल हो रही है.
Should not be.
Okay, sir. Okay, carry on.
Sure. I mean, first of all, again, I would like to thanks to Dr. Sajid Sajjad. I mean, I always used to say it's a Sajjad or Sajid, right? Sajid. I just mixed up. It's Dr. Sajid Sajjad. Thank you for inviting me for this wonderful webinar, and especially in these days, it's a big thing because we also have been organizing these conferences for the last few years at the Department of Physics, GC University, Faisalabad, and Dr. Sajid has been here in Faisalabad and presented his work. And I know it's a lot of pain and a lot of it's just like headaches to organize these things, whether it's like on the internet or on the in presence. So I hope that this initiative from Dr. Sajid Sajjad and his team and his Vice Chancellor of Dawood University of Engineering and Technology, who has supported him, and obviously without the support of the high-ups, such events and other big achievements, they are not easy to achieve. So thank you, all of you, and congratulations, because this is my last talk. Congratulations on managing this successfully and smoothly in a very good way. So as all the participants, they can see my screen. My name is Adnan Ali, and I'm working at the Department of Physics, GC University, Faisalabad since 2012. And the topic of my presentation or my talk, that is on rapid identification of bacteria using a hybrid plasmonic platform, or we can call it SIRS. To elaborate the SIRS, it's surface enhanced Raman spectroscopy. And this is some layout of my presentation. NBRC is Nanomaterials and Biosensing Research Centers that we have established here with the help of my my seniors and my colleagues. We are working here. Even right now, I'm if I can show you people, I'm just sitting in the XRD lab. Actually, I've been working in the lab right now due to the talk, so I've come here. So this is one of our labs where we have the access, and this lab is open for collaboration for everybody. There are many other techniques people can use and access. It's not only the X-ray diffraction. So in NBRC, Nanomaterials and Biosensing Research Center, our research is basically divided into 2 to 3 categories. We can divide. We are doing the biosensing, and in the material science side, we are working on the thermoelectric materials, measuring their thermoelectric potential to use them in conjunction with solar cell. And the other aspect is solar cell device fabrication. It's not exactly the like the fab labs that many of us have seen in abroad. It's not we don't have that clean room where we do the fab. It's basically p-n junction formations and thin film transistors we are doing here in our lab. So in the biosensing aspect, the history of this biosensing, because we are in the physics side and how we ended up in the biosensing, it's because of the project of Dr. Khalid Mahmood, one of my colleagues in NBRC from the PARC US project. The grant was 50 million, it's 50 million PKR, Pakistani currency, and it was with the Professor Yang She at the University of California, Los Angeles, and from there we got the training on the micro Raman PL system in the Korea back in 2018. We completed this project up to 2 years, and we are extending this project by working on different aspects, by detecting the pathogens and some other things that organic molecules mostly using this SIRS method. So I'm just giving this a brief introduction of my group and all the other research activities, because research is like joining hands. So we need to join and shake hands to move forward in Pakistan, because there are the facilities, the lab facilities, they are not like in advanced countries. So that's why I'm sharing all these details. So anybody who can come to us, they can have our details, our contact details from Dr. Sajid Siala as well. My email was in the beginning of my presentation, so we can all of you are welcome to collaborate, or we can work with us. These are our team members: Professor Dr. Nasir Amin and Dr. Khalid Mamoon. Third one is myself, then Dr. Kashif Javed, Dr. Salma Ikram, and Dr. Sophia Akbar. And these are some of our research grants. Dr. Khalid Mahmood, we received 50 million grant. Myself, I received 10 million research funding. Dr. Nasir Amin, 7 million. And Dr. Sophia Akbar, recently she received 100 million PKR. These amounts are not in dollars, it's in PKR. So these are some of our research publications. Data of the last 2 years, 2019, we have 27 publications, and in this year, 2020, we have 32 research publications. And beside this, I have also been the guest editor of Physica B and Superconductivity and Novel Magnetism Journal. So these are some of our characterization and growth facilities: chemical vapor deposition system, thermal evaporator. So to fabricate, this is our some high vacuum thermal evaporator system. It's connected with diffusion pumps and other rotary pump with a couple of gauges to measure the vacuum. Or another chemical vapor deposition system. And we have these are our muffle furnaces. And the left one, it's 1200 centigrade. The middle one is 1600 centigrade. We can give different gas treatments. And the right one is 1400 centigrade muffle furnaces. So if anyone is in need to perform annealing or sintering or any other process or in different atmosphere, then they can contact us. They can use these facilities because generally the furnaces are 1200 centigrades, not up to 1600 centigrades. And this is our biosensing lab that we have established because there were a lot of things that were related to the biology and some biochemistry terms. We tried with the help of our other colleagues from other departments and tried to learn and develop these things. With this, this whole lab is separated, and before going into this lab, we need to change and have to wear this coveralls. We are doing this back in 2018 because by then we were dealing with some, we were measuring SIRS spectra on tuberculosis bacteria, which is an airborne pathogen. So we have to deal with all the precautions and have this fume hood with some incubators and centrifuge machines. And this is our micro Raman PL system. This is equipped with 2 lasers, 633 nanometer. It's actually 632.8 nanometers and 785 nanometer laser. The reason for using these 2 wavelengths is because 633 nanometer is red color wavelength and 785 is in the infrared region of the electromagnetic spectra, and they are close to these wavelengths. They are close to the organic structures, molecular vibrations. So that's why we need the IR and red laser to measure the structure of pathogens of the cell walls or any other organic structures. So that's why we have these 2 lasers, and in the same system we can measure the I was looking at one of the slides of Abdul Malik Qurasha. He was explaining the photoluminescence in a very good way. So we in this system we have these 2 lasers for photoluminescence as well, and but for photoluminescence of semiconductors and some wide band gap semiconductors, we should have lasers around 532, 525, 514 nanometers, or 248 nanometer, or 325 nanometer wavelengths for wide band gap semiconductors. Because if we have to use these 633 nanometer or 785 nanometer wavelength, we can only probe the band gap of materials. That's around 1.12 or 1.15 eV electron volts. So we cannot go beyond that for the photoluminescence with these lasers. And this is our scanning electron microscopy setup. And one of our students is operating this electron microscope. And another thing that I have to share, all these machines are operational, and this is like up and running. There are no, alhamdulillah, there is no issue with these machines as such, because only there are machines lying idle in the labs and not functional. So this SCM, it's also, this is from M-Crafts from Korea. It has very good resolution. If anybody is interested, they can send their samples to us for the measurements as well. So we can give them their measurements. It's the XRD machine that I've shown you, even that I'm still sitting in this lab. We're just working on measuring some samples. This is Bruker D8 Advanced. So we can use thin films and powder materials or polymers or any other kind of materials to investigate their crystal structure. And this is also this is functional. It's working right behind me right now. So if anybody needs that, you can access us. You can send the samples to our address as well. Department of Physics, GC University Faisalabad. Just write my name on that. They can send it. And this is another interesting system for the thermoelectric measurements. We can measure high temperature thermoelectricity of materials, right? So we can calculate the power factor, not the figure of merit. If anybody is among the audience who has background in the thermoelectric materials, he or she should know that for the measurement of figure of merit, we need to perform the electrical conductivity. We need to perform thermal conductivity. We don't have that, so we are limited by that setup. But I'm very hopeful that soon we shall have that setup as well. And this is some photocatalysis setups. Some of our students working on that. This is our LIBS setup. It's not connected with the chamber. The laser is it's ND-YAG laser, 1032 nanometers with its harmonics to 266 nanometer. It can generate those harmonics. And this was our introduction about our labs and some facilities that we have at NBRC, Nanomaterials and Biosensing Research Center. So let's briefly talk about Raman spectroscopy. What is Raman spectroscopy? I've told you that Raman spectroscopy is a vibrational spectroscopy technique, right? We're an incident laser that falls on the molecule, and we can have these three Raman scattered light with scattered signal. Its energy is greater than E naught, incident light. Energy is equal to E naught, it's Rayleigh scattered light, and less than E naught, it's Raman scattered light. So we can have two signals, vibrational signals, and based on that, we can see here. One is called Andy-Stokes, the other one is Stokes. So we're generally looking at the Stokes because if you look at this one, it has higher energy. So higher energy means it's a shorter wavelength, and lower energy means its wavelength is higher, because the energy and wavelength, they are inversely proportional. So this is one of the schematic diagram of our, in general, it's a Raman system where the laser falls on a mirror, and the mirror it sends to a beam splitter, and then the laser is focused through a lens assembly onto the sample, and the signal goes back from the sample through the lens assembly to the beam splitter, and then to the focusing lens, and then through the gratings into the spectrometer and to CCD for the detection of these signals. And these are some of the lasers that I have talked about earlier, that there are different lasers are available, and for different Raman system, the reflection or the optics for these lasers, it's entirely different. So we are only working with red laser and IR laser. I mean, obviously we cannot look at the IR. And these are some of the variants of Raman spectroscopy. So we have normal Raman spectroscopy. Generally, we do that where we put the sample and then we control it with the computer and turn on the light, and it gives the spectra. So we can look at that. The other is the surface enhanced Raman spectroscopy. So when we say the term surface, surface means we are actually using the plasmonic effect. Plasmons, what are plasmons? Plasmons, it's we imagine it like a combined oscillation of the charges, that combined oscillation of the charges that originates or give rise to the plasmon. So if there are no free charges that can oscillate, so there will be no plasmon. So generally these plasmons are in like in metals, gold, silver, copper. So these metals, their surfaces, they have high concentration of electrons, and they're the combined oscillation of electrons that give rise to the origin of plasmons. The third is chip-enhanced Raman spectroscopy. So we only worked around with this surface-enhanced Raman spectroscopy. Yes, what is SIRS? If we look at that, laser light falls on the analyte. Analyte is the molecule that we are probing, and there's a Raman scattering signal and the Rayleigh scattering. Rayleigh scattering is always stronger because its energy is equivalent to the incident light. Raman scattering, it's always the weak, and generally these are the phonons that are being generated that we are looking at. If we look at this structure, where that molecule is in close vicinity of some metallic nanostructures, right? So when the light falls on this analyte or the molecule, organic molecule that we are looking at, so we can see that the Raman signal is enhanced. It's enhanced if we compare it with this signal. It's not enhanced. And so that's the beauty of the research, that we can enhance the Raman signal from the organic structures to an order of magnitude 10 power 7, 10 power 8, 10 power 10. So we can go up to those enhancements. So because of that, SIRS, or this phenomenon, has the capability to detect single molecules. So we can detect single molecules. So based on that, we can imagine that we can detect the explosive materials if there is very slight concentration of those molecules or those material. If it is being present in something, we can even there are some applications of SIRS that whether the meat or beef available in the market, the source of that beef or meat, because we don't know whether it is coming from some haram animals or those animals that are forbidden, or some halal source. So we can use SIRS to detect that as well, and we can even use it for the detection of some chemicals that are being mixed up in, for example, in milk. So we can detect that as well. What else is added in the milk by using the SIRS? And besides that, we can use that SIRS for the pathology and for the pharmacy, in the pharmacy section as well, the SIRS, because as I've told you, it's a vibrational spectroscopy technique, and we can use it for multi-purposes and in different fields as well. Some of the, I mean, again, it's the basic diagram how the SIRS is working. So the principle of the SIRS, it's very easy to understand. If you look at there's in the metals, there is an electron cloud, and when the laser light, which is an electromagnetic radiation, when it falls down on those metallic nanostructures, so what happens? The electron clouds it moves away. So there's a polarization, there is an oscillation because of that. And this oscillation is the electromagnetic enhancement. That electromagnetic enhancement actually gives rise to the enhancement of the Raman signal. There's another enhancement of the Raman signal in the surge phenomena that is called chemical enhancement. Generally, chemical enhancement doesn't have that higher strength as compared to the electromagnetic enhancement. Electromagnetic enhancement has very high intensity. And these are the suitable materials that we can use for surge applications, and for copper, gold, and silver. For the copper, we can look at the wavelengths if we are working around these, and that's on 600 to 1200 nanometers, and for the gold is the same. For silver, it's 400 to 1000 nanometers. Another thing that I would like to share as well is that if we, because there are a lot of people who are working in on the synthesis of silver nanostructures, so with different nanostructure, with different shapes, the surge signals is different, right? So if people are working on the optimization of these nanostructures for the surge applications and for the reusability of the surge as well, because if we can reuse the surge, that would be much better instead of having some new surge substrate, which is another, that's a drawback of the surge. It's expensive when you look at the fabrication procedure, especially using the clean rooms of category 100 or even 1000. So it's expensive to fabricate the surge there. So, but it's cheap if we look at the synthesis process. Let me share the slide. Some of the fabrication methods, generally there are many fabrication methods, but generally we haven't worked all over these methods. We only have worked only a couple of methods for the fabrication of surge. So I was talking about the fabrication of surge, that it's very expensive. If we, what happens if we work on, I mean, like if you go around this top down. The top down is it's an expensive thing if we go like that. But if we use, if we go from bottom up approach, it's just cheap because we are using the chemicals for the synthesis of these nanostructures. We are using some salts, then going through some hydrothermal reaction or some sol gels or some sintering process, and then we form the nanostructure. So that's a cheap route. And the another drawback of the surge is the repeatability. So if the surge is good, having very good signals, so we have to make sure the signal is repeatable. For running the experiment again and again, it should give us the same results. So that's because the Raman signal is very sensitive. So that's one of the drawbacks with its repeatability. These are the gold nanopyramid fabrication for surge that we have used here, and the process is lithography, and there's a photolithography that has been used in these. Graphene is another candidate instead of using these metals, or we can use graphene in combination of gold nanoparticles. The combination of graphene and gold nanoparticles, it enhances the surge signals very, very high. So if we do not use graphene, we are using gold nanoparticles. So the signal is still good. But if you use graphene, signal is like boom. This is too good. So we can look at that over here as well. See here, we are only using this. There are two gold nanoparticles. The signal is coming from these two, which is being wasted here. With the use of single layer graphene, see, so the signal is going higher because the graphene itself, it has a good capability of generating the plasma, the surface plasmas. So that is one of the reasons that 2D materials, they have found their way in another application of that's in the surge, besides some other optoelectronic devices where graphene is being used or being tested, investigated. So these results, these are our own lab results, these SEM measurements that we did here at our with our own microscope at the GCUF, and so we did that measurements last year. It's 2019 here. So this is the surge substrates over here on the top left. and these spots, these are the solutions containing pathogens. These are the bacteria. And this region is the gold particles, and the other region, this one, where we have put a drop of containing the pathogens. It is on the graphene. So in the SCM images, you can see that these dots, these are the nanopyramids of gold. And the other thing that we can see on the surface, these are the E. coli bacteria, right? And the remaining dark color is the media that comes along with it. So the other alternate was a choice besides, because gold is expensive, silver is expensive, copper is not expensive, but copper is not good, that much good, if we compare it. So alone graphene is, we cannot use alone graphene for the SIRS because the combination of both graphene and gold is a very good strength for the SIRS. So these are some other alternative materials, and we have actually synthesized these materials by using hydrothermal method in our lab here, and tin selenide, molybdenum selenide. We have used these, and we are testing these materials for their SIRS capability. But as far as what we have seen, these tin selenide and molybdenum selenide, in this current form, they were not giving us some good SIRS spectra. So what we did, we are now working on their surface functionalization, bio-surface functionalization. I mean, this is more accurately, because the bacteria, they cannot attach to the nanoparticle. It's an organic structure. The cell wall of the bacteria, it has the lipids in it, some high lipid or lipoprotein structures. So it cannot attach to the metallic structures. So we need an alternate, some mediator in between. It's like the linker, something that attaches the bacteria with the molecule. So we are working on this aspect to attach the that linker to attach the bacteria with the molybdenum selenide or tin selenide nanoparticles, and then to perform the SIRS using. These are our own results on ZTO. ZTO is zinc tin oxide nanostructures. We use these as to test their SIRS capability, and we have seen that at 600, 700, and 800 centigrades, we can see we have good spectra from E. coli. E. coli is one of the safe bacteria to work around. And next is zinc germanium oxide. It's another material that we have tested here in our lab for its SIRS capacity. But here we didn't use, in this one on the left one, we didn't use bacteria. It's methylene blue, and the right side is E. coli. And we can see that we have some good fingerprints from the E. coli bacteria. So in generally, the pathogens we can test all these pathogens to test them using SIRS. So, I've mentioned that single molecule detection have been reported as well using SIRS. So the bacteria, they have been classified based on these three, based on their shapes, like the spiral shape, bacilli, and coccus. And we have been using this E. coli in our lab, and we developed this culturing here in the physics lab as well, taking the patient sample from the lab with the consent, and then from the culturing, and then this streaking we did here, and then perform the gram staining. Gram staining actually let us know that it's a gram positive or gram negative based on their cell wall composition. And this is the TB bacteria that I've told you. We have worked on that project, and we were actually developing that database for the tuberculosis bacteria for the SIRS database of tuberculosis bacteria, because the TB bacteria, unfortunately, if anybody get that disease or So the treatment or even the testing, it is very long. The cell culturing for tuberculosis bacteria, it's around 6 to 8 weeks. It's almost 1.5 months to 2 months. So with the help of this surge technique, that time can be reduced to less than a month, so which is quite less, and then it can be diagnosed based on that. So we build a database for that, and we have been performing the staining protocols for that, Xyl, Nilstein staining protocols for the acid-fast bacilli in our lab, and some of the media details, how we can grow these bacteria on different media, because we need to grow them. The bacteria need energy. They have to, I mean, just like humans, they need glucose and some protein structures to grow. So these yellow structures, these are the colonies of the tuberculosis bacteria in this media. And generally we pick those bacteria, prepare a solution for these, and then put them a drop of this onto the surge substrate. And this is the my last slides. These are where mapping is performed, because without mapping, it's very hard to look at the bacteria, because the system we have, it has the optical microscope up to 50x. I mean, it's 50 times it can go enhance the image. So we have to select a certain region, as you can see in this cross, this red color, and then we have to select the step size, how much step we have to take from one point to another point and then along the x-axis and along the y-axis. We have to define the steps. So, and then we perform the mapping on this certain area, and that takes around hours. It generally takes, with a smaller step size, with a better resolution, it takes around 6 hours, 4 hours to 8 hours. I mean, generally, but if we take the larger area for the mapping, the time goes very high. It's like 10 hours, 12 hours, or a day as well. Like the whole day, like 24 hours to perform the mapping. So we can see in the mapping, the laser has hit the bacteria, and we get this signal. And this is one of the spectra from the mapping area for E. coli, and to look at their features. So when we look at these images and in the Raman, this is Raman spectra, but we cannot get this Raman spectra without having that surge structure, because we have to put the bacteria in this. We should have a bacteria in the solution, because we took it from the cultured plate that grown on the media and put the drop of 1 microliter or 2 microliter, a drop containing bacteria onto the surge substrate. So surge is graphene, gold nanopyramids, silicon dioxide, silicon. Is this assembly? So if you put that drop of bacteria on a glass slide or on simply a silicon surface, we cannot see even this spectra. You might be looking at a straight line or some noise or very high fluorescence. We cannot look at these sharp peaks. So that can be studied. So all these peaks, they are actually describing the different cell wall structure, composition, carbon-carbon mode or carbon stretching mode. So these are again some data on the tuberculosis. This is the Mycobacterium tuberculosis, and this is the multiple drug resistance tuberculosis bacteria that we have tested in our lab under the safe conditions. And the last thing, it's very important. So this is the principal component analysis. Without this, all the effort, all the hard work, it can be wasted if we do not learn this thing. Because this is one of these, as a sample graph taken from this source. So we look at, there are some 3 different species, right? So blue, orange, and green. Without PCA, if we do not perform this, the whole data is mixed up. So by performing PCA, it can differentiate among the different strains of bacteria, because all the bacteria, their cell wall composition is not much changed. It's almost the same. If we're talking about gram positive, if we talk about gram negative, all the gram negative, they have the same composition, right? So we need to perform the PCA. PCA helps to differentiate between these different species. So, and the last one is, these are our conclusions, and the conclusions post that we can detect organic structures, pathogens, solutions, or explosives, or anything organic, or even semiconductors or metals, material, anything we can use or to study using Raman, SIRS, or TERS. The process is very simple and fast, but it's all based on the SIRS substrate or the hybrid plasmonic platform. And thank you for listening to me patiently, and I'm again thankful to the organizing committee, Dr. Sajid Sial and his team, and his dean of the school and his vice chancellor for making this event possible in these days where traveling is not likely. I mean, people just avoid to travel in these days. So maybe in some other good circumstances, would like to be there and have a one-on-one or face-to-face conversation and presentation. And thank you.
Thank you very much, Dr. Saab. Thank you very much for your precious time. Really, I appreciate in this evening. It's very difficult for everyone that they spare some time, especially for these events. And inshallah, we love to see you in Karachi physically. And inshallah, we hope we'll serve you in a very better way. If there are any questions from our participant sides, so you may ask from Dr. Saab. Dr. Saab is a very cooperative and very wonderful personality of our country. So
thank you.
Even there is some appreciation words from the Yunus Talpur Saab. We appreciate your efforts regarding this. Even Saib, he also say something about your presentation, very great manner. If there are any question, you can ask. Then we will go for our concluding ceremony. Because we are officially going to close the ceremony with a very best regards and with a very best memories from yesterday. And I hope all enjoyed this session of today, even yesterday's session. So if you want to say something about general idea regarding Dr. Adnan Saab, in the perspective of this symposium, over to you, Dr. Saab.
Thank you, sir. As I've stated again that in these circumstances where traveling is not likely, I mean, everybody likes to travel. So initiating this event, I would again suggest that you can with this experience on the webinar, you can move on to some more specialized areas. I mean, as based on your metallurgy or material sciences or some other specific applied seminars that you can go for that. So that would help again to select the community, to communicate with each other, and especially in Pakistan where facilities are limited. So we need to work around how we can move forward with those limited facilities. So the best way is to join hands, to shake hands. So that's the best way we can move forward because we always have to work within our resources. With the limited resources and with these efforts that you have done here, I mean, there are more than I think you have registered more than I think close to 1,000 participants. So I know not everybody is available, but they have the access to all this to these talks. So all of us, we should come together, work together, and with all the facilities, with all the ideas, the whole community, it moves forward. So I would suggest that we should, inshallah, and that this pandemic would end soon, and all of us that we can move around freely without using those masks and hand sanitizer. I've been using every day many times this hand sanitizer. So
thank you, Dr. Adnan. We are expecting, Dawood University also expecting a very great cooperation from your side, even your side, and as well as Dr. Abdul Malik Saab from the PIAS, even from the Islamic International University, because as you know that Dawood University became a full university in 2014. So sometime our Vice Chancellor said that we are still growing our baby university. So we expect that inshallah in future we will get benefit from the all resources of Pakistan as well as from abroad, and with a whole community of researchers, even well researchers in Qaid-e-Azam University, GC University Lahore, GC University Faisalabad, Mehran University, ND University. It's a time we have worked together for our community, for humanity and other peoples. In this way we can grow, and then we will help other globally. If we are first on a one page, then of course Pakistan on a bigger screen with the help of all researchers and even the scientists.
yes, you are right. It's in need of the hour as well. And I didn't know that the university was established in 2014. I thought it's an old university. So
okay.
Yeah.
Yes, I'm going to connect Dr. Manzoor Saab from Islamabad. Dr. Manzoor Saab is the chief guest of today's session from President of ECO Science Foundation Islamabad. So I'm trying to connect. Give me only the 2 minutes. There's Dr. Saab is waiting for me, because sometimes we are facing some troubles for connecting the people. So I'm trying to connect Dr. Saab. Wait a moment, sir. Wait a moment. I apologize from all of you that. अदनान साहब थोड़ी देर तक आप जारी रखें, kindly. It's my request. Adnan Saab?
Hello.
Keep it continuous, as I am taking our chief guest on online. So over to you, sir. You engage our worthy participants as well.
Okay. Yep. Why not? So they can hear me?
Yes. Everyone hear you, sir.
Okay. So I was sharing about these. I'm assuming that they're the people with different backgrounds. Mostly people are working in the material sciences areas, and I was sharing about our.
Sir, John. Ji Adnan Saab, keep continue, sir. Adnan Saab, please.
Okay, so I want to extend the cooperation that all these are facilities in our labs. Anybody in Pakistan and even abroad. In fact, I can share that even some of our students who have been to China, they have been sending the samples. It's not like that, because once they tell me that there is a long queue, because of the long queue, they send the samples. Even sometimes they bring the samples with them to perform the measurements. So these facilities, these are for the people of Pakistan, for this community, for the young researchers who want to access these and want to work forward. If they have some good ideas, so we can sit and work together. And further, there were two more things that I have missed. That very soon we are going to have vibrating sample magnetometer. It's VSM, and a lot of people who are working in the field of magnetic materials, they can access this VSM at our lab, Department of Physics, GC University Faisalabad, to measure the magnetic characteristics of their magnetic materials. And another aspect that we are going to add in our lab is the pulse laser deposition system. We are going to have it very soon in our lab. So these are the two instruments. I hope with the help of these two instruments, not only our the students in Pakistan, in different universities, they can have the access to these, and they can use these instruments for their research. They can come here. They can even stay here as well for a few days to perform their research activities. So all of you, you are encouraged to come to visit. Whenever it's visible, they can access me at my email address. It's adnnan_1982@yahoo.com. They can access me, or if they have some samples to measure, they can do that. And another thing that also I missed in my presentation is the simulation aspect. We are also doing the device simulation. Device simulation, it's not the DFT. It's a DFT is different. So we are doing the device simulation. Device simulation, we generally try to optimize the devices like solar cells, lasers, or optoelectronic devices. We generally use those softwares for this purpose. And the software that we are using, it's SCAPS, PC1D, PC2D, and there is another very good software is Nanonext. It's a very wonderful software to use for the simulation of devices, and we have the access to that software, the licensed version to do the simulation. So thank you all.
Thank you very much, sir, Adnan sir, for supporting Dawood University, Karachi. Now I'm going to officially start concluding ceremony with the recitation of Holy Quran. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم ألم تر كيف فعل ربك بأصحاب الفيل ألم يجعل كيدهم في تضليل وأرسل عليهم طيرا أبابيل ترميهم بحجارة من سجيل فجعلهم كعصف معقول صدق الله العلي العظيم. Now, heading towards the concluding ceremony of a great event which we call as a National Multidisciplinary Symposium on Advanced Technology and Allied Fields of Dawood University of Engineering Technology, as well as in Pakistan. I would like, and we tried our best to perform the well and give a good part to our newly researchers and the scholars. Here, I want to tell you one thing. I'm pleased to inform you all, more than 800 people applied and registered for this symposium. And here is a top class keynote speakers were with us, including Dr. Muhammad Zahir Iqbal from the GIK, Dr. Khusro Dubash from the Lahore, Dr. Shumail Ashraf from China, Dr. Muhammad Sufyan is from Faisalabad as well as Jiran University, China. Dr. Ehsan Ejaz from Mirpur University of Science and Technology, Azad Kashmir. And today's session, a great scholar and the keynote speakers, Dr. Hafiz Muhammad Asif Javed Saab was with in the morning, afternoon session, and Dr. Bushra Ahmad Khuram Sahiba from the University of Karachi. Even the Islamic International Professor Sardar Sikandar Hayat Saab from the Department of Physics joined us, and one of our best keynote speaker, Dr. Abdul Malik, as a principal scientist, joined us as a keynote speaker, and not in the end, Dr. Adnan, as you sir, also joined us as a keynote speaker our session. I'm really very grateful to you, and I'm thank you everyone for being and participating very actively and listening us very carefully. This symposium is an excellent example of inter-academic and cooperation, because we have, I'm really grateful to all the participants as well as our team, our IT team. They are 1 minute to minute also supporting me and also giving some path. Even there is a lot of difficulty we are going to face when you are doing some online session. So, but we are taken very cleverly. And now I am going to give a space to our worthy Pro-Vice Chancellor of Dawood University of Engineering Technology, Dr. Abdul Wahid Bhutto Sahab, to give you say something about this program. And thank you to all. Sir, over to you, Dr. Abdul Wahid Bhutto Sahab.
Thank you, Sajid Syal Sahab, and good afternoon to all audiences. They are online here. I am thankful to all our resource persons and key note speakers for their valuable inputs and contributions for this 2-day symposium, a multidisciplinary symposium on advanced technologies and allied fields. The number of audience who attended this 2 days event shows it was a very well organized and a well planned event, and they get a good attention from audience throughout the country. It's a great success, not only for the Department of Materials and Metallurgy, but it's a good success for Dawood University as well. Organizing a webinar is always a very difficult task, because this is a paradigm shift in culture in educational sectors in Pakistan, because in normal circumstances we usually have arranged these conferences in a physical form. After COVID, all universities are facing a new challenge, how to continue operating effectively, addressing the key issues the society is facing, while also taking precautions of COVID. So I am once again like to thank the department, and these types of seminars provide directions to faculty, departments, and scholars to set their priorities and prepare policies and strategies for next medium term and long term. So I hope this 2-day event will help our departments, our faculty, and our postgraduate students to align their work with the latest developments going on around the globe in the field of materials and nanotechnology. I am once again thankful to all participants, and I must congratulate and must acknowledge all organizers, especially the chief organizer, Dr. Sajid Syal, who is also the chairperson of Department of Materials and Metallurgy. Thank you, all participants. Well done, Sajid Syal. Thank you.
Sir, we are waiting for our chief guest of today's ceremony, Professor Dr. Manzoor Hussain Sumro Sahab, President of ECO Science Foundation. And they have some connectivity issue. So sir is also willing to join us this ceremony and want to say something about. So we are waiting for a few minutes for his joining, sir. Ji sir. Dr. Abdul Malik, our keynote speakers of today's talk, I would like to say something about this program, sir. Abdul Malik Saab, over to you, Abdul Malik Saab. Dr. Abdul Malik Saab from Apyas, principal scientist of our country. Dr. Abdul Malik Saab. Sir, मेरी आवाज आ रही है आपको? Hello. I would like to invite you again in our ceremony, sir. So welcome you again, sir.
Thank you very much. Thank you very much. About this symposium, I am glad to share about it was a very appreciable and actively and highly successfully holding event. And also from my side, I also hope that after approval we will able to proceed with the negotiation regarding MOU signing to strengthen the material domain envelope and benefit from the generous cooperation and expertise of DUE team.
Thank you very much.
I also want to add about the facilities at in our department. Lot of facilities, I think, most sophisticated throughout in Pakistan. The facilities like molecular beam epitaxial growth system, LPCVD, and many of other advanced system, FTS, CM also, and other laser. These are the material driven facilities, but also there are in the laser most advanced, and the system they can the participants or the researchers can work here in NILO. So all facilities from our side is open for all throughout the Pakistan. About the lasers, lid systems, spectroscopy, very advanced system, and also we can characterizing at a large scale like magnetic properties also. Okay, ji, hello.
जी sir.
Dr. Saab.
जी sir, continue करें sir. जी sir.
So these some of the researchers, some of the students from your universities, and can join in our labs, do their research work, and use these advanced facilities to for the for the nation. So I hope in future we will collaborate in such a way that students from your university